serves as an assistant professor in the Department of ECE at NIT Rourkela. NIT Rourkela. He has obtained his PhD in electronics engineering from ISM Dhanbad. He has published his works in 10 journals, 11 conference papers, and one book chapter. His research interests encompass all facets of semiconductor devices, ranging from material physics to device design and modeling, and extending to device circuit co-design for a diverse array of applications. He's currently involved in two sponsored projects. He's currently leading the research group on advanced nanomaterials and nano devices at NIT Rourkela. Thank you so much for joining us, sir. So please, the screen is yours.
Thank you. Okay, thank you very much for the nice introduction. So first of all, I would like to thank Professor 𝗕𝗫𝗄𝗎 for inviting me, and also Professor Ipsita. Okay, so can I start now?
Yes, sir.
Okay, is my screen visible?
Yes, sir, visible, sir.
Okay, thank you. Okay, so let me start with a small introduction of myself. So once again, I am Dr. 𝗕𝗵𝗂𝗃𝗍. So I am assistant professor in the Department of Electronics and Communication Engineering at NIT Rourkela. So today, I will be basically discussing about on a very specific topic, that is the design and modeling of semiconductor quantum cascade detectors for infrared and terahertz detection. I will be discussing about the recent trends and the future prospects. Let me hide this toolbar. Okay. Now it is clearly visible, right? My PPT?
Yeah.
Am I audible?
Yes, sir, audible.
Okay, thank you. Okay, so I was telling that today I'm going to discuss basically on a specific device that is called quantum cascade detector. So from the name, one can guess that this device basically will be working to detect the photonic wavelengths, and the application will be in the infrared and the terahertz wavelength detection. So I'll be majorly focusing on the device part, and then I will be discussing some of the design challenges associated with this particular device and how in our group we have addressed these challenges. So my presentation is outlined as follows. So first, obviously, I will be discussing about why we need a quantum cascade detector. Then I will be discussing what is a quantum cascade detector, what are the advantages of this particular kind of detector over the conventional photodetectors. So what are the current challenges and how in our group we are addressing these particular challenges and some of the future direction, obviously. So let us start with the definition of a quantum cascade detector. So what is a quantum cascade detector? It is basically a special kind of photon detector. It is made of multiple quantum well structures. So those who have studied the basics of semiconductor physics, they can easily correlate what is a quantum well. And in this quantum cascade detector, we have multiple quantum well structure. And this particular structure is applicable for the infrared and the terahertz wavelength radiation detection. So to further understand how this quantum cascade detector works or what is the structure of this quantum cascade detector, so let us first understand why do we need basically this quantum cascade detector. So to understand that, so let us first take a very basic photodetector structure. So to understand the working of a conventional photodetector structure, we are taking a semiconductor material. So here in this diagram, we have a semiconductor material, and we know that semiconductor materials are basically characterized by a valence band, which is completely filled at absolute zero temperature, and we have a conduction band, which is normally empty at absolute zero temperature. And on this semiconductor material, if we illuminate light of the semiconductor material, and if the light energy is higher than the energy band gap of this material, what will happen? The electrons from the valence band, they will absorb this photon energy, and they will move from the valence band to the conduction band. And in this process, there will be generation of electrons in the conduction band, and there will be generation of holes in the valence band. We call this as the electron hole pair generation. And these carriers, these electrons in the conduction band and the holes in the valence band, they will be working as a carriers, and we call them as photocarriers. Now, if by some mechanism, if we can collect these carriers, the free electrons from the conduction band and the holes from the valence band towards the contact, and if we connect some external load to this semiconductor material, what will happen? There will be a flow of current to this external load, and we call this current as the photocurrent. So this is the process how the current is generated due to the illumination of light. And the important thing is that this photo absorption can be of three types. The first type is that there may be the interband photo absorption, and where the first thing here we can see the electrons from the valence band, they are absorbing the photon energy and they are moving from the valence band to the conduction band. So we will call this as a interband photo absorption. Then this photo absorption can be assisted by some defect state in the energy band gap. So the absorption can be from the defect state to the conduction band, or it can be from the valence band to the some defect state. Or the third process can be the absorption of energy, photon energy, by the electrons from a particular band. It may be valence band, it may be conduction band, and it will move in the same energy band from a lower energy state to the higher energy state. And we will call this kind of absorption as the intraband absorption. Now, out of these three absorption processes, the first two processes, they may generate the photocarriers, and these photocarriers can be collected by some methods, and we can get some photocurrent. Now, the third process basically doesn't give you any extra carriers to give you the photocurrent. So, the first two processes are very important, and our conventional photodetectors basically works on the first process, that is the interband photoabsorption. So from the definition, one thing we can observe is that the detection wavelength of the radiation that basically depends on a particular energy Eg. Say this Eg is the general term. So this Eg, it can be the energy band gap of the particular semiconductor material. It can be the distance, it can be the energy difference between the valence band to the defect state, or the defect state to a conduction energy band, or if you have some Schottky junction kind of devices. So these Eg may be the barrier height. Now in conventional photodetectors, so this energy is basically the energy band gap, and we know that by using the conventional semiconductor material, this energy band gap cannot be very small. And for the infrared and terahertz wavelength radiation detection, this energy should be very small. It should be in the order of few milli-electron volt. So by using the conventional technique or conventional semiconductor material, we cannot achieve the detection in the infrared and the terahertz wavelength region. And also, so one of the carrier collection mechanism, here we can say the carriers which are generated by the photon absorption. The carriers which are generated by the photon absorption, they are basically collected by a process called the diffusion of the carriers. And if you apply some external electric field, so there will be drift of the carriers. And this drift and diffusion process, it is a slow process. So normally for this conventional photodetector, we have a slow response speed. And also, most of these photodetector, they works under photoconductive mode, where we apply some external voltage, and due to this externally applied voltage, we get the photocurrent. So even when you don't have any external light illuminating on the semiconductor material, due to the application of this voltage or external electric field, we will be having large current, or there will be movement of carriers due to the externally applied electric field, and we will be having some current flowing through the device, which we call as the dark current. So for the conventional photodetector, we will be having the large dark current. So these are the challenges with the conventional photodetector. So how we can solve this challenge? We can use the nanostructures by using this semiconductor material. So we'll be doing some engineering on this using this semiconductor material, and we will be designing the nanostructure to get some novel devices. And we can use a transition technique that is called the inter-subband transition. So to further understand these techniques, let us first see. So the first diagram here, we have a bulk structure. In bulk structure, we know that electron can easily move in all the three directions. And where if you look at the PK diagram, we have a continuous energy energy dispersion along the K in the conduction band and in the valence band. But if you have a nanostructure, here we have, I have shown the example of a quantum well structure. So in this quantum well structure, what we have? We have a narrow energy bandgap material. This green region is a narrow energy bandgap material, which is basically sandwiched between two wide bandgap material. Now, when we have this narrow bandgap energy bandgap material, so we can easily control by depending on the growth process, we can easily control this L. And when this L is very small, so how small it should be? It should be less than the de Broglie wavelength of electron in this particular semiconductor material. And if L is less than the de Broglie wavelength of electron in this particular semiconductor material, we will be observing the quantum confinement effect. It means that electrons along the z direction, it will not be able to freely move along the z direction, where it will be having no movement restriction along the x and the y direction. And due to the restriction of the movement of electron along the z direction, there will be quantum confinement effect. And due to this quantum confinement effect, the continuous energy band, it may be conduction band, it may be valence band, it will be splitted into energy subbands, right? And this energy difference, it will be basically depending on the material parameter as well as this L. So by controlling this L, we can control the energy difference between this E1 and E2. So there will be multiple energy levels, and depending on the thickness of this narrow energy bandgap material, we can control the energy levels in this particular quantum well structure. And if you can, so one can easily guess, so this conduction band difference between the narrow bandgap and the wide bandgap material, it will be very small. And inside this conduction band or valence band quantum well, we have the formation of the discrete energy levels. So if we can, so the energy difference between the corresponding energy levels will be very small. So we can have the detection in the infrared and the terahertz wavelength radiation, because this energy difference will be of the order of few milli-electron volt. And the transition, if we have transition between these energy levels, so that transition will be called as the inter-subband transition. So if we can use these kind of energy levels, and if we can make the transition, basically optical transition, means due to the external light energy, if we can make the electron move between these energy levels, so we can use this particular structure to detect the light. So based on this, we have the first or very famous device that is called the quantum well infrared photodetectors. So here you can see, here we have the schematic diagram for the quantum well infrared photodetector. So here, basically, we have multiple quantum well structure. We have seen how the quantum well is formed. So here you will be having multiple quantum well structure, and the dimension and the material of these quantum wells are taken in such a way that so for here we can see there will be two energy levels, and depending on the energy difference between these two energy levels, we have the detection wavelength. And the design will be such that the ground energy state will be fully occupied by the electrons, and the upper energy state, or what we call as the first excited state, that will be in equilibrium. That will be at the edge of the quantum well. And when we apply, so here this diagram basically tells you the energy band diagram. When you have some external applied electric field, when we apply the electric field, what will happen? The first excited state, it will be in resonance with the continuum energy state. So when you illuminate this structure with the photon energy, so the electrons from the ground energy state, they will be excited and they will move from the ground energy state to the first excited state, depending on the wavelength of the radiation. And from there, due to this energy continuum and due to the application of the external electric field, the electrons from the upper excited or the first excited state, they will be collected by the contacts. Now, in this process, we can have the infrared detection. But the problem is that the energy difference between these energy levels, the ground state and the excited state, it is very small. It is of the order of few milli electron volt. So what will happen? And also here we have some external electric field applied. So what will happen under dark condition, when we don't have any light illumination, the electrons from the ground state, they can be thermally excited and they can move from the ground energy state to the upper energy or first excited state, from where, due to the application of this electric field, they can be easily collected and they will generate a very large dark current. So we have quantum well infrared photodetectors and they are capable for the detection of the infrared wavelength radiation. But the problem is that at some finite temperature or even at room temperature, there will be a large dark current. And due to this large dark current, to make a efficient detection of the photon energy, we need a arrangement that is called the cryogenic cooling is required, right? So we have to operate these devices at the cryogenic temperature. And we know that this cooling arrangement will be very difficult to make a device compact for different applications. So what could be the solution? Solution is the use of the special device, which is also made of these multiple quantum wells, which is called the quantum cascade detector. Now, this quantum cascade detector, it is also a multiple quantum well semiconductor heterostructure. Now, here we have a schematic diagram of the energy levels corresponding to a quantum cascade detector structure. So here you can see we have the active region. This active region, it is basically a single quantum well, or it may be a couple quantum well, and it followed by a extractor region, which are basically multiple quantum wells. Now the engineering here is that the active region is basically responsible for the detection of the light energy. It means that, so from the design, this active region, it is a quantum well structure where the region will be heavily doped, so that the ground energy state will be occupied by the electrons. And depending on our requirement, we can choose the dimension of this active region quantum well in such a way that it will support, it will make the transition from the ground state to the first excited state, which will be equal to our desired wavelength of detection. And this region is followed by this extractor region. This extractor region is multiple quantum well structure, and the dimension of the quantum wells are taken in such a way that the energy levels, so these lines are basically the energy level representation. These energy levels, the difference between the energy levels between the quantum wells, they will be the difference will be of the order of yellow phonon energy, or we can say phonon energy of that particular semiconductor material. And when we have this kind of design, what will happen? So when we illuminate this structure with light, the electrons from the ground energy state, they will absorb this photon energy and they will move from the ground energy state to the first excited state in the active region. And from there, what will happen due to the design of this extractor region, where we are making the energy difference between the corresponding energy levels equal to the phonon energy. So the photo-excited electron from the excited state in the active region, they will get a preferred path for the transport, which will be supported by the yellow phonon scattering mechanism. So due to this phonon difference between the energy level, it will form a phonon ladder. And due to this phonon ladder, the electrons from the excited state of the active region, they will undergo through the yellow phonon scattering mechanism. And through this scattering mechanism, they will be transferred to the next period for this quantum cascade detector structure. So here, one thing we can observe is that without applying any external bias voltage, due to the design engineering of this heterostructure, we have a preferred flow of the carriers from left to right, and this flow of the carriers is basically due to the yellow phonon scattering mechanism. So due to this design, this device can be operated under zero electric bias voltage. So we can have basically photovoltaic operation. And when we have the photovoltaic operation, we can expect that there will be very less or zero dark current. So when we have the zero dark current noise, so it will basically simplify the design of the readout integrated circuit. And the next thing is that here, due to this photovoltaic operation, we can achieve room temperature or even higher temperature operation of this quantum cascade detector structure. And here the transport is based on the inter-sublime scattering. It was in the traditional quantum well infrared photodetector also. So this inter-sublime scattering mechanism, they are a very fast process. So you can have a very high speed detection by using this kind of quantum cascade detector structure. Then one important thing for this quantum well devices is that for traditional or for conventional photodetector, if you want to change the detection wavelength, we have to change the semiconductor material. But here, only by changing the quantum well thickness, we can have different wavelength detection. And even by doing some engineering of these quantum waves, we can have multiple wavelength detection in the same device. So that are the advantages. Now, so we have the advantages of these quantum cascade detectors over the conventional photodetectors and over the traditional quantum well infrared photodetectors. But even in these quantum cascade detectors, there are a lot of challenges to design this quantum cascade detector to make it perfect, to make it more efficient. There are a lot of challenges that one can face, and some of the challenges we have faced, and we have proposed some solutions. So first challenge is with the device design. So here we have the energy band diagram and corresponding energy levels and the wave function for three different quantum cascade detector design. The first design, it is made for 3.88 micrometer. So this wavelength is basically decided by the energy difference between this active wave state A1 and A2. And it is of the order of 319 milli-electron volt. So it will be able to detect 3.88 micrometer wavelength radiation. So these three structures, they are the experimental structure. The second structure, this structure is basically designed for 17.39 micrometer and 4.26 micrometer. And the third structure, it is basically the designed to detect the terahertz wavelength, and where the wavelength is 90 and 77 micrometer. Now, from this diagram, one can easily observe is that the design of this particular device, it basically requires the accurate energy band solution for this whole heterostructure where you have multiple quantum wells, and also the information of each of these energy levels along with the wave functions, right? So the challenge is that To basically design or study this kind of devices, one has to accurately calculate all these energy levels and the wave functions and also the energy band diagram. And also the transport in these devices, it is very complicated process. We are telling that the electrons will be excited from the ground energy state to the first excited state for the active region. This region is the active region, and from here they will be collected to the next region by the electron scattering mechanism. But that is not very simple process. So that is one description. But here the quantum wave structure, the any question?
No, sir, there were some disturbances, so
Okay.
please continue.
So here, one thing we can observe, the thickness of these quantum wave regions, they are very small. They are of the order of few nanometer. So there will be transition of carriers between each and every stage. It is not very simple that electrons will be excited from A1 to A2. The electrons can be excited from A1 to any of the other states. So here, the transition, the carrier transport is a very complex process, and there is no commercial software available to describe the transport or to calculate the energy band solution for the structures. So the first problem that one will face to study or design this kind of devices is that there is no availability of the commercial software. So you have to design your own software to study this kind of devices. So challenge one is that so accurate energy band solution is required, and challenge two is that the carrier transfer through these devices is a very complex process. So you have to get a very simplified design to describe the carrier transfer through these devices. The first solution, so we can have the self-consistent solution of the Schrodinger-Poisson equation taking consideration of this particular device structure. Then the second solution is the simple transport model. So in literature, one can find that there are basically two transport models for this quantum cascade detector structure. One is called thermalized cascade model. Second one is called thermalized subband model. But both of these models, they fail to describe the quantum cascade detector performance in the light condition or the illumination condition. And for a wide range of temperature, they cannot provide a proper description of the quantum cascade detector characteristic. And the next thing is that in these theoretical models, they have only considered that the endophonon scattering is the only scattering mechanism that is responsible for the carrier transport through the structure, which is not true at all. So to get a more accurate model that can describe the quantum cascade detector characteristic under dark and the light condition for a wide range of temperature, we have proposed some transport model that can solve all of these problems. So from the quantum cascade detector structures that are already fabricated and some of the theoretical papers also, we observe that the energy difference in the extractor region quantum wells, they are basically of the order of electron energy of that particular quantum well material. But the energy difference between the first excited state in the active region and the energy state of the first quantum well in the extractor region, that may be equal to the electron energy, or that may be very small to get the more efficient extraction of the photoexcited carriers from the active region to the extractor region. So we identified that the transport of the carriers from the active region to the first extractor well region, it is basically due to two processes. One is due to the resonant tunneling process, and second one is due to the scattering tunneling process. So after getting after getting extracted from the active region excited state to the first quantum wave straight in the extractor region, they will be basically moving through a yellow phonon scattering mechanism, because it will be the dominant scattering mechanism, because the energy levels difference is nearly or equal to the yellow phonon energy of that particular material. So to design the transport through this particular quantum cascade detector structure, we have followed very simplified rate equation model. And how we have incorporated the rate equation model in the design of the quantum cascade detector. So here we have identified the transport mechanism. Then we have identified what are the major scattering mechanism that basically gives the transport of the photo-excited carriers through this quantum cascade detector structure. And we observe that yellow phonon scattering, it will be dominating, but at the same time, this active region is heavily doped. So there will, due to this doping, there will be ionized impurity scattering. And here we have the multiple electron system. So there will be the electron-electron scattering also. And also, we have the heterostructure, and we know that the heterostructure interfaces cannot be perfectly smooth. So there will be obviously interface roughness scattering. So we identified, so we have taken many scattering mechanism, and we identified that these four scattering mechanism, they are basically dominating scattering mechanism, and they basically help for the transport of these cathode excited carriers through these quantum cascade detector structure. So one more thing. So in a quantum cascade detector, we have the active region, we have the extractor region, and this active region and the extractor region, they together form a single period of the quantum cascade detector. And for the detection of the photon energy, this period is repeated multiple times to get the a better detection. So when we have, so A and B, they are the basically two period of the quantum scale detector. So there may be multiple periods, right? So there may be periods, there may be some quantum wave structure before this A, after this B. So there are a lot of quantum wave structures. So there are a lot of energy levels. Now, if you want to model the transport of the carriers in a particular period of these quantum scale detectors, so one can observe that there will be transition of carriers between each and every energy levels in the between the quantum waves in the period A, and there will be also transport of carriers from the energy levels which are in the quantum waves of period B to the quantum waves of period A. And if there are some periods available before this A, there will also be some transition of carriers from the period before this A also. So here we can see there is a very complex transport mechanism involved here. So to simplify this model, to simplify this transport mechanism, what we have considered that the carrier transport from the next period and the previous period will be more significant, and the transport of the carriers from any other periods which are beyond this period B, or which are beyond the periods. Say here you have a period A prime. So before that period A prime, so there will be very less interaction of the energy levels, and there will be very less transport of the carriers from those periods also, right? So we have, so if you can only take the period A for which we want to model the transport, and the next period B and a previous period, say A complement, right? Now, when you want to model the carriers transport in this particular period A, we have to take additional two more periods, that is B, and say there will be another more period, that is A prime. Now, this is a periodic structure. This quantum cascade structure is a periodic structure, and there is a symmetry between this period B and A prime. So if you can only take these two periods A and B, we can model for this whole 3 periods. And how we are doing this? So here these solid lines, they basically gives you the transport between the energy levels in the period A as well as between the energy levels in the period A and B. And this dash line, they basically represents the transition of carriers from this A period to the previous period, that is A prime. By this way, we have basically removed the period A prime in the modeling purpose. And if you can only take this period A and B, these two consecutive periods, we can basically model the carrier transport for the whole system. So we have taken the rate equation formalism, and in the rate equation formalism, we have defined the rate of change of carrier in each of these energy levels of this particular period A, for which we want to model the carrier transport, right? The first equation, it basically gives you the carrier dynamics in the energy levels of the extractor or of the active region excited state. So here, let me show you again. So here you can see this one, it is the ground energy state for the active region, and this 5, it is the first excited state where the detection will happen. So the energy difference between 1 and 5 gives you the detection wavelength. So 5 is the first excited state for the active region where the photo excited carriers will move from the ground energy state to the 5th state, right? And from where they will be collected by these energy levels 4, 3, 2. Then this 1 plus, it is the ground state of the active region for the period B, right? And then there will be again excitation from 1 plus to 5 plus, then they will be again collected by the next period, right? So to define the equation for the state number 5, it is not 5th state, it is the state number as 5. So here the carrier will be moving from this excited state to the extractor well state, and this movement may be the resonant tunneling transport mechanism or the scattering tunneling transport mechanism. So carrier will be because they are moving from this region, this excited state to the extractor well state. So this resonant tunneling transport is minus here, and then all these minus signs, they are basically the forward transport where the carriers are moving from this particular excited state in the active region to the other states. And these plus signs, they are basically representing the backscattering or the carriers which are moving from any of the other states to the excited state. So here, the first term, it is due to the resonant tunneling transport term. This second and the third term, it is due to the intra-period transition, means the transition that is happening inside the same period. Say, for example, the period A that we for which we want to design our carrier transport, and these two basically gives you the transport of the carriers from the next period or from the previous period. So this is called the intra-period transition, and this is for the inter-period transition. This is for the level 5. And again, so from our previous diagram, so the 4 was the first energy levels for the first extractor well state. So for the 4th state, if you design, so here this resonant tunneling transport current density term, it will be added in the carrier dynamics, and the rest of the terms will be similar to our first model equation. And for all the other states, we can simply write down this equation by removing this resonant tunneling transport current density term. And here, all these tau term, they are basically the scattering time, and the scattering, it combines the radiative scattering as well as the non-radiative scattering. And here in the non-radiative scattering, we have identified that this yellow photon scattering, interface sharpness scattering, and the ionized impurity scattering. They will be dominant scattering mechanism. Here we have neglected the electron-electron scattering mechanism. And because we have seen that electron-electron scattering mechanism will be significantly smaller, and it has a very less contribution to the overall scattering rate. So we can easily calculate all these scattering rates if you have the information of the energy levels of this quantum mechanical structure, as well as the wave function associated with each of these energy levels, and that can be obtained from the solution of the 𝗕𝗏𝗄𝗏 equation for this whole structure. And if you can calculate the scattering rates, so we can easily solve the rate equation that we have defined previously. So by using the numerical methods, we can solve those rate equation, and we can have the steady state solution of those rate equation, which basically tells you the number of carriers, steady state carriers in each and every energy levels. And if we know the number of carriers, from there we can define many parameters associated, many figure of merits associated with this particular device structure. So such a parameter is that for this quantum mechanical detector is that responsivity, so which is defined as the photocurrent density to the incident optical power. So this photocurrent density, it can be calculated by taking the difference of the forward transition to the reverse transition of the carriers that is flowing between two consecutive periods. And from there, if you can find out how many carriers are effectively getting transported from period A to the next period B, from there you can easily calculate the photocurrent density. And after getting the photocurrent density, we can easily calculate the responsivity. And we can also, so here, due to this photovoltaic operation, the detectivity is basically the thermal detectivity, which is termed as the Johnson detectivity. And this Johnson detectivity can be obtained by using this relationship, where R is the responsivity and R naught A is the resistance area product for this particular device structure, and this R naught A can be easily obtained in the dark condition. So, so to obtain this R naught A product, we have applied a very small external voltage, because at a smaller applied voltage, so we expect that this voltage versus current relationship will be linear, and from there we can easily obtain this resistance area product. By applying a very small voltage, we can find out the dark current, and from there we can find out the resistance area product, and by using this resistance area product, we can easily obtain the Johnson detectivity. So okay, so here we have designed one 𝗕𝗏𝗄𝗏 solver using so by using some numerical methods, and for this particular structure, where we have only taken two periods of the quantum cascade detector structure, and we have solved the 𝗕𝗏𝗄𝗏 equation, and we have obtained the energy levels and corresponding wave functions. And we have observed that our calculated energy values and the experimentally observed energy values, they are nearly matching. So here we can see at also our model, it can easily take the consideration of the temperature on the energy band. So here at 5 Kelvin temperature, the calculated energy difference, so this energy difference, it is basically the energy difference in the active region energy states. So it is 125.9 milli-electron volt for the calculated one, and for the experimental, it is 127 milli-electron volt at 5K. And for 300K, so it will reduce to 124.2 milli-electron volt, while the experimental value is 123 milli-electron volt. So we have some experimental accuracy which can be justified from these values. And after getting these values, after getting the energy levels and the wave functions, so we can calculate the scattering rates by using the Fermi's golden rule. And after calculating all the scattering rate, we can use some numerical method to get the steady state solution for this differential equation, which are the rate equations. And from there, we can obtain, we can get the values of the steady state carrier numbers for each of these energy levels. And from there, we can find out the responsivity and the detectivity performance. And here, these plots basically to verify our model with the experimental results. So here we can see that there is some sort of matching with the experimental results with the calculated values, and also the trend is similar to the experimental result. So from here we can use our model to design and analyze the quantum cascade detector structures. Now, the next challenge that we have faced is that the performance of these quantum cascade detectors, they basically degrade at higher temperature because the material system that we use, or which are used for the design of these quantum cascade detectors, they're basically 3-5 material system, where the commonly used materials are gallium arsenide, aluminum gallium arsenide system. It may be indium gallium arsenide, indium aluminum arsenide system, or indium gallium arsenide, aluminum arsenide antimonide system. So the problem with this material system is that the transport of this quantum cascade detector structures, it is dominated by the yellow phonon scattering mechanism. And the yellow phonon energy for these material systems, it is of the order of 30 to 40 milli-electron volt. And at some finite temperature, what will happen? The electrons will have sufficient thermal energy, and they can get excited from the ground state to the upper state, and the performance. So even at the even without some illumination, even at the dark condition, there will be sufficient amount of the current flowing through these devices. So the performance will degrade at high temperature because we have a very less electron energy for this device structure, for these materials that are used for the design of these quantum cascade detector structures. So here the solution can be in the form of using some different material which will be having higher electron energy. Such material is that third nitride materials, and for third nitride materials we have the electron energy of the order of 91 to 99 milli-electron volt, and also the conduction band offset. So here these devices that we are designing, they are designed inside the conduction band or inside the valence band. So if you have a larger conduction band offset, so we can have a range of wavelengths starting from a very small wavelength to a very large wavelength can be detected by using this quantum cascade detector structure. And third point is that the carrier relaxation time in this third nitride, it is smaller, or in terms of scattering, relaxation scattering, we can say that the carrier scattering, relaxation scattering for this third nitride heterostructure, it is faster compared to the other third 3-5 materials. It is of the order of 170 to 370 femtosecond. And when we have the carriers are getting transported by very fast carrier relaxation mechanism, so we can have a very high speed detection also. So by using this third nitride, one can have a very high speed, low noise, high temperature device operation with outstanding responsivity and the detectability performance. Some of the designs are available in the literature, and these third nitride materials, they are applicable for the near infrared to a very short infrared, and also even for the terahertz wavelength radiation also. But again, here we have another challenge. The challenge is due to this material structure. So here this third nitride material structure, when they are used in the urdite crystal structure, they are basically affected by the two polarization. One is called the spontaneous polarization due to the atomic structure, and second one is due to the lattice mismatch which is the piezoelectric polarization. And due to this piezoelectric and the spontaneous polarization, which are the internal polarization fields, the solution of the Schrödinger-Poisson equation becomes very difficult. And also this quantum cascade detector structure, it is a periodic structure, and each of the periods are having multiple quantum wells, and these quantum wells are also asymmetric quantum wells. So due to this problem, what will happen? The design of the quantum cascade detector structure using this hard nitride material is very difficult. And so here we have the problem due to this spontaneous and the piezoelectric polarization fields. So there, each of the periods, energy levels, and the wave functions, they will be affected by the these polarization fields, and as well as the electric field, which are originating at some other period of this quantum cascade detector structure. And obviously, to get that detection, we have to dope some of the quantum wells with the with some kind of dopants to get the electrons at the ground energy state. And due to this doping, there will be obviously space charge effect. So we have to get a very accurate solution of the Poisson equation to consider the polarization effect and the space charge effect. And also, normally, if one searches for the solution of the Schrödinger equation for the quantum wells, so if you have a single quantum well or the multiple quantum well structure, when we try to solve the Schrödinger equation for this structure, we basically take the hard-wall boundary condition. Hard-wall boundary condition means whatever structure we are considering, so at the boundary, we consider that the wave function will be zero at that particular boundary, and this is called the hard-wall boundary condition. And when we take the hard-wall boundary condition, it may happen that if the structure is not limited by the quantum wells that we are considering for the solution of the Schrödinger equation, it may happen that electrons electron wave functions and the electron energies, they may spread over the entire structure. So it will give you some inappropriate solution of the Schrödinger equation, and the energy and the wave function that will obtain, that will be different from the actual values. So we cannot use the hard-wall boundary condition for this quantum cascade detector structure, because this quantum cascade detector, it has multiple quantum wells, and it is also periodic structure. So here one solution can be obtained in the form of using a periodic boundary condition. So here we propose a solution that will be fully self-consistent, and where we will be using proper boundary condition for this particular third nitride material. So here we have the one, we are taking the quantum structure. So we have a one-dimensional Schrödinger wave equation, and here this mz. So here we are also taking the effective mass, which will depend on the position, because we have the heterostructure. And for the Schrödinger equation, we are taking the four potential term, that is 𝗕𝐶𝗔, 𝗕𝗔, 𝗕𝗏, and 𝗕x. So where this 𝗕𝐶𝗔, it is the conduction band offset term, and this 𝗕𝗏, it is due to the externally applied electric field. So it is considered by using the external electric field, that is F. And this pH, it basically takes the internal polarization fields as well as the doping of the structure. And by solving the Poisson equation, we can obtain the this potential, and we can include in the Schrödinger equation to get the solution. And this Vx, it is for the electron-electron interaction term, and it is modeled by using this exchange correlation potential, that is Vx. And after calculating all these values, we have solved this Schrödinger wave equation by using a discretization method that is called the finite difference method. And by using this finite difference method, we have discretized the Schrödinger wave equation, and we get this matrix form. And by using the periodic boundary condition, actually we have modified this equation where these two terms will be added. And after getting this matrix equation, one can have the eigen solution, and in the eigen solution, the eigen values will give you the energy levels, and eigen vectors will give you the wave functions corresponding to that particular energy levels. And to get the solution, we have to again obtain that VH term. So in this equation, this VH term, it depends on the internal polarization fields as well as the system doping. So once again, you have to properly obtain this VH, and after getting this VH, you have to solve this Schrödinger wave equation. To get this VH, you have to solve the Poisson equation, and in the Poisson equation, we have to take the carrier density of each of these energy levels for a particular for each and every quantum wells, and also we have to take care of the doping. So if you have if you have designed the device in the conduction band, so we have a donor kind of doping to get the electrons in the ground energy state. And again, this Poisson equation is also discretized using the finite difference method with the proper boundary condition. And here the boundary condition, we are taking the interface boundary condition and the periodic boundary condition. And the interface boundary condition, we are taking the electric field boundary condition. So this electric field displacement, it is made equal to the polarization difference between the two materials at the interface. And this, by taking this boundary condition, this Poisson equation is again discretized. And we have also taken the final boundary condition, that is the periodic boundary condition, which is reads like this. So Vz plus Lp. Lp is the dimension of a single period of the quantum mechanical detector. So it will be Vz plus EFLP, where EFLP, it is basically due to the applied electric field per period. So this periodic boundary condition will be there, and by taking this periodic boundary condition and after discretizing the Poisson equation using finite difference method, we can use the numerical methods to get the solution. So the algorithm, self-consistent algorithm, is like this. So first we have to get the material parameters, and we can calculate some of the polarization fields. And after getting these values, we are taking the initial potential value as the conduction band offset and the externally applied electric field. After getting this V, we can put this V value in the Schrödinger equation, and by taking this V value, we can solve the Schrödinger equation by using some eigenvalue solver, from where we can obtain the energy levels and the wave functions, and from there we can obtain the Fermi energy level corresponding to the structure, and from where we can get the carrier population. After getting the carrier population, or we can basically calculate by using the internal boundary condition. We can solve the Poisson equation. By solving the Poisson equation, we can get this VH term. And after getting this VH term, the potential will be updated. So here this old potential is basically VCZ and VEZ, and then we have added this exchange correlation potential. Then this VH, it accounts for the internal polarization fields and the doping of the quantum wells. So after updating this new potential, so this loop will be repeated multiple times to satisfy the this condition. So here we have the condition, that is when the difference between the new potential and the old potential is less than 10 to the power minus 6. So we have the final solution. So after getting this self-consistent solution, one can go for the design of the quantum mechanical detector structure or some other device structure that that can use this kind of particular solution, and one can analyze the performance of these devices. So here from our solution, we have obtained this kind of energy band diagram for this third nitride material. So here you can see in the quantum well and the barrier region, we have opposite kind of energy band bending, and this energy band bending is due to the internal polarization fields. So these first two structures, they are basically reported structure in the literature. All these three structures are the reported structure in the literature. So we have used our own solver to solve the Schrodinger-Poisson equation, and we have obtained this energy band diagram, and we have verified our results with the literature results. Some are experimental, some are basically use some other methods to get this Schrodinger-Poisson solution. And we have obtained that for the quantum cascade laser. So this QCL, it stands for the quantum cascade laser design, and QCD stands for the quantum cascade detector design. And both of these structures, one is the laser structure, another one is the detector structure. Both are based on this quantum cascade structure, right? So for quantum cascade laser design, we have obtained that experimental result is 21.8 millielectron volt when we take the energy difference between the E3 and 2, and our calculated value is 21.6 millielectron volt. And for other design also, we can see that there is a very close matching with the reported results and the experiment, our calculated results. So we can use our solver to design the devices and to analyze the performance. So for this third nitride quantum cascade structure, we have studied the optical performance. Basically, we have studied the absorption, photon absorption in this quantum cascade structure, and we have obtained the absorption coefficient with respect to the doping of the active region, as well as the variation of the temperature. And one thing we observe here is that for this third nitride material, here you can see in this third diagram, so this absorption energy variation is very less, significantly less. So here you can see for a variation of 250 Kelvin temperature, the absorption energy is varying by a very small amount. So from here, one thing we can basically establish is that by using this third nitride material system, we can have temperature independent detection of the photon energies. So based on that, we have designed one particular device basically for the photon detector, and this device will be applicable for the detection of the photon wavelength for the optical communication. Basically, we are designing this device for the 1.5 micrometer wavelength. So here we have the design structure. So this gallium nitride, it will be working as a active region, followed by this aluminum nitride, aluminum gallium nitride multiple quantum well structure, and this structure will work as an extractor region. So this aluminum gallium nitride, it will be the quantum well for the extractor region, and the aluminum nitride, they will be the barrier region. And by using this design, so we have basically obtained the performance of this particular design for the detection of 1.5 micrometer radiation. So we have obtained the Schrodinger-Poisson solver for the 2 consecutive period, that is period A and A plus, and we have obtained the energy levels and the corresponding wave functions very nicely. And by using this obtained energy levels and the wave function, we have used our transport model for this quantum cascade detector structure, and we have obtained some of the performances. So these are the basic equations one can easily find in the literature. So from our design, we obtained that the variation in the responsivity over a temperature variation of 400 K is only 2.16 milliampere per watt, when we use the third nitride material to design the device. And another thing, the photon energy variation is only of the order of 3.26 milli-electron volt. So here we have a comparison with the literature available devices with our device. Any question? Okay. Okay.
No,
so one thing we observe here from this table, one thing we can see. This second column, it is basically tells you the percentage variation of the responsivity over a 200 Kelvin temperature variation from 100 to 300. So here for all the other designs of this quantum cascade detector, we have a very huge variation of the responsivity performance. But by using this third nitride quantum cascade detector, that is our design for this optical communication application, that is 1.5 micrometer wavelength, there is a very small variation, only 7.37%. And then we have performed some analysis, and we found that this interface roughness scattering, it is a very major scattering mechanism, and it basically after the electron scattering mechanism, this interface roughness scattering mechanism basically dominate the transport mechanism. And we have studied why it happens, how it happens, and then so these results are very, very basic results. So we have the important thing is that the for this quantum cascade detector structure, the transport modeling was very important, and the second point was that to get the accurate solution of the Schrödinger-Poisson equation was very important. And after getting those solutions, one can easily obtain all the other results, and one can easily verify all the other results. So here we have the responsivity variation with the different thicknesses of the extractor barrier, then active region well, and we often how they basically affect the responsivity performance of that particular quantum cascade detector design. Now let me discuss about the next challenge. So when we use this C-plane 𝗙 material, so we are seeing that there is a huge effect of these internal polarization fields, and due to these internal polarization fields, so design of this quantum cascade detector for different wavelengths, it becomes very difficult. So for quantum wells, we have seen that by varying the thickness of the quantum well, we can control the detection wavelength, or we can control the energy sub-band energy levels in that quantum well. But due to this internal polarization fields, we have seen the energy band bending in the quantum well and the barrier region. So we have a triangular like potential, and to get the proper design for for different wavelengths, it is very difficult to control. It is very difficult to accurately tell for which dimension will be having this particular required energy difference. So the design of the quantum cascade detector structure for different wavelength is becomes very, very difficult when we use this C-plane 𝗙 material. So what could be the solution? So in literature, one can observe that there are so if you grow the third nitride materials along the non-polar direction, these problems can be solved. So in non-polar direction, we can have M plane and the A plane, which are basically experimentally studied. And out of these two planes, M plane nitrides provide best results in terms of surface roughness. So roughness will be smaller, inter-subband absorption will be higher, and also the absorption time width will be smaller. And for this non-polar third nitride material, we have proposed two designs. One is based on the scattering tunneling transport design, and second one is based on the resonant tunneling transport design. So here we have shown for the two consecutive periods. So here is the active quantum well and followed by the extractor well, which is having two quantum wells. And here also we have another period of the quantum detector structure. And we already have discussed that if you have the information of the energy levels and the wave functions for the two consecutive periods, you can easily describe using the rate equation models that we have proposed the performance of this quantum detector structure. So here we have the design that is called the scattering tunneling transport design. Why it is called scattering tunneling transport design? Because the energy difference between the active region excited state and the corresponding energy levels of the extractor region state, they are basically exactly equal to the yellow phonon energy of this particular material. And by properly selecting the dimension of these each and every regions, we can design this kind of structure. So here the electrons will be excited from where they will be collected by the yellow phonon scattering mechanism. And second design is the resonant tunneling transport design, where you can observe that the excited state in the active region, it is in energy resonance with the extractor region quantum well state. So there is a strong coupling between the excited state and the extractor well state. So the transport will be governed by the resonant tunneling transport. So electron will get excited, and from where they will be transported to the first extractor region state through the resonant tunneling transport process, and from where it will be transported to the next period through the scattering tunneling transport process. So out of these two designs, we have again used the basic equation and our rate equation model, and we have obtained the responsivity and the detectivity performance. And we observe that when we use these non-polar structure, so by using the scattering tunneling transport design, there is a 50% variation in the responsivity over the temperature variation, while the resonant tunneling transport design gives the higher variation compared to the scattering tunneling transport design. But the responsivity value for the resonant tunneling transport design is higher compared to the scattering tunneling transport design. And the detection wavelength, so here we have a very important point that detection wavelength variation is small. So we can have the temperature stable detection wavelength or temperature stable detection by using these structures. Then we have obtained the detectivity variation, and we find that that detectivity. So here we can see the resonant tunneling transport design shows higher detectivity performance compared to the scattering tunneling transport design, but the variation is large here. So after doing this design, we have obtained another problem. The problem is with the design of this quantum detector, where we have to use the inter-subband absorption mechanism, and we know that when we have the inter-subband absorption, so it is the limiting factor for the detection of the photon energies by using this quantum structure. So which we cannot change much by using some design aspects, because this inter-subband transition we have to use for the detection of the wavelengths using this quantum detector structures. But the second problem we have that the carriers which are excited by the absorption of the photon energy, the extraction has to be 100%. But when we have this kind of design, the extraction of the photo-excited carriers is less, and due to this less photo carrier extraction, we have a low responsivity performance. And why it is less? So here from this diagram, one can observe the carriers will get excited from the ground energy state to the excited state, and from where they will be collected. So this is called the extraction. Now here we have this quantum wave structure where the ground state and the excited state, they are at the in the same quantum well, and there is a strong coupling between the excited state and the ground energy state. And when you have the overlap between the wave functions, so there will be obviously some relaxation scattering between these energy states. And if this relaxation scattering is sufficiently high, it may be comparable to the escape scattering rate. So what will happen? So the extraction of the photo excited carriers will be less, because many carriers will get excited, then they will get relaxed before getting extracted. So we have to reduce this relaxation scattering mechanism. So how we can reduce this relaxation scattering mechanism? So if you can reduce this relaxation scattering mechanism, we can increase the escape probability, and if you can increase the escape probability, we can basically increase the photo detector gain. Now, how we can reduce this relaxation scattering rate? So there are some design. In the literature, the first design is use of the diagonal transition design. So here, what they have done, they have used two coupled quantum well structure, where the ground state will be in one quantum well, and the excited state for the active region will be the next quantum well, and they will be obviously strongly coupled. And when you have this kind of design, so here you can see the overlap between the wave functions is getting reduced. And when the overlap is getting reduced, the scattering rates basically depends on this overlap integral of the wave function. So obviously the relaxation scattering rate will get reduced. And when this relaxation scattering rate gets reduced, so you will be having more extraction of the photo excited carriers. So by using this design, they have obtained almost 70% of the extraction of the photo excited carriers, and the responsibility is obviously limited because there is less overlap. So the excitation, that is optical transition, will also reduce. So responsibility is 16.9 milliampere per watt at 300 Kelvin at 8 micron detection wavelength, and also the detectivity is also getting reduced because we have to use this coupled quantum well design in order to get this diagonal kind of transition. So responsibility is getting reduced. The next design which is presented there is that use of strongly coupled quantum wells, where they are basically using the resonant tunneling kind of transport through this quantum well detector structure. But here, due to the strong coupling between the quantum wells, the extraction is getting improved, but at the same time, the noise, the dark current is also getting reduced because there is a strong overlap between the active region states and the extractor region states. So here responsibility they have obtained as high as 166 milliampere per watt, but it is obtained at a low temperature. And its detectivity performance is obviously degraded, and the room temperature operation is also not possible by using this kind of structure. And the third design, they have used the localized electric field by applying some doping, shallow doping in the quantum well region and the barrier region. And by using this doping, they have created the local electric field to get this kind of energy band bending. And by using this kind of design, they have obtained almost 89% of the extraction of the photo excited carriers. But again, due to this strong coupling of the quantum well energy states, so this performance is limited only at a very low temperature. So here for this case, it is only 80 Kelvin. So compromising the room temperature operation, obviously detectivity performance will also degrade. So so these are the literature the designs, and by using this design concept, we have proposed one design. By using a step quantum well structure, we can improve the extraction probability for these photo excited carriers. So what is a step quantum well? So here you can see we have a narrow energy band gap material which will act as a active well, and which followed by a little higher energy band gap material which will be working as a step barrier, and followed by the final barrier which is a large energy band gap material. So if you have this kind of quantum well structure, we have a few advantages. The first advantage is that the ground energy state, if the ground energy state is in the active well and the first excited state, it is in the active well and the state barrier well. So one can observe that the wave function for the first excited state, it will be basically confined towards the state barrier. And due to this reason, the overlap integral between the energy level 1 and 3, it will get reduced. So here we have advantage of the diagonal design, but at the same time, we have the advantage of the coupled quantum well design, because after this state barrier, if you design this kind of coupled quantum well, due to this smaller, we can make this barrier between the extractor well and the active well smaller. Okay, so if we can make this barrier smaller, so there will be strong coupling between the excited energy state in the active well and the extractor well energy state. But at the same time, so the effective barrier between this active well and the extractor well is this step barrier as well as the final barrier. So what will happen? The coupling between, or the coupling between the active region ground energy state and the first extractor well state will be strongly reduced. And due to this reduction, what will happen? This kind of transport will not be allowed for this step quantum well coupled quantum well design. So we have many advantages. So due to this design, we have a reduced non-radiative scattering due to the reduction in the overlap integral between the wave functions of the active region states, and also we can have an increased extraction efficiency, because here the coupling between the extractor well energy and the excited state energy of the active well is getting increased, but at the same time there is a reduction of the coupling of the ground energy state of the active well and the extractor well region is getting reduced. So we can have reduced dark current and increased detectivity. And using this structure, so here we have the basic rate equation, basic scattering rate equations, and we have first we have solved the Schrödinger-Poisson equation for the step quantum wells, and then we have obtained the optical performance of these step quantum well structures. So here the main result is here. So we have calculated the escape probability for the step quantum well design, and we obtain that by changing the step barrier width, we are basically increasing the escape probability. So when we increasing the step barrier width, the relaxation scattering rate is getting reduced and the escape probability is getting increased. So this is the important result that we have obtained. And based on our observation, we have again designed two design for this quantum detector structure. So design 1 and design 2. So they are almost similar, and the difference is that the excited state, the excited state here, it is here the energy state in the extractor well state, it is below the step barrier. But here for the design 2, the energy levels in the extractor region, it is above the step barrier, and due to this, the coupling between the excited state in the active region and the extractor well energy levels, it will be more for the design 2, where the coupling will be less for design 1, and when the coupling is higher, obviously for the design 2, the escape probability will be higher. So same result we have obtained, that escape probability as high as 85% can be obtained for the design 2. So this is the important observation that we have obtained. So after this, one can basically design the whole device structure and use this rate equation model to observe the responsitivity and the detectivity performance for these photodetectors. So this was the final observation that we had. So in future, one can easily one can design a complete quantum cascade structure by using the state quantum well. Obviously, they can use multiple material system. They can have the design for the very long wave infrared region as well as the terahertz wavelength radiation. And also, they can make the design for the improved responsivity performance. So with this, I would like to end my presentation here. So if anyone has any question, they can ask.
Thank you, sir. Dear participants, do you have any questions for sir? Do you have any questions? Sir, actually, I have some questions.
Yes,
Hello.
yes, please.
Sir, actually, what are the softwares you have used for this work?
Yeah, software. So as I have already mentioned, there is no commercial software available. So obviously, I have used some programming platform. I have used MATLAB to basically code our analytical equation or the numerical methods. So only the MATLAB or any of the programming software like Python, MATLAB can be used to model all these things, but there is no particular commercial software available to design this kind of devices.
Okay. So you have done programming.
Right.
Okay. Sir, what about, sir, have you used console, multi-physics software?
COMSOL, yes, for this structure, you need the information of the energy levels and the wave functions, and I don't think COMSOL will be able to give you the proper solution for these structures.
Okay. Yeah. Okay, sir. So, dear participants, do you have any questions? Any questions, please? Okay. I think there is no question. So, thank you so much, sir, for delivering such an insightful and engaging session. We truly appreciate the time and effort you have devoted to sharing your knowledge with us. On behalf of Dr. Kshitij and myself, Dr. 𝗕𝗬𝗪, we extend our sincere gratitude and wish you continued success in your academic and professional endeavors and looking forward to host you again. Thank you so much, sir.
Thank you.
Thank you, sir.
Okay, so may I leave now?
Oh, sir?
May I leave now?
Yes, sir.
Okay. Okay, thank you very much.
Okay, sir. Thank you so much, sir. Okay. Hello, 𝗕𝗃 sir, are you there? Okay. Dear participants, please wait for 2 to 3 minutes. Sir will join in very short time. Hello,
Really?
sir, are you there?
Can you hear me?
Yes, sir. Yes, sir.
Yeah. So let me share my screen.
Okay, sir.
சார் பயங்கரமான கிஃப்டா இருக்குதே.
Okay. Okay. Welcome, sir. Thank you for joining us, sir. So, today, so this is our actually last day of our FSFM 2025, and we are heading towards session 11 and session 11. And for this session, we have Professor 𝗕𝗵𝘃𝗧𝗏. So, Professor 𝗕𝗵𝘃𝗧𝗏 is a distinguished professor in the Department of Physics at IIT Kharagpur, West Bengal. He obtained his PhD from the Indian Institute of Science, IISc Bangalore, and carried out extensive postdoctoral research at Princeton University and Rutgers University in the USA, as well as in Grenoble, France. He has held key professional positions at Harishchandra Research Institute, HRI Allahabad, and IIT Kharagpur. Professor 𝗕𝗏𝗃𝗧𝗏 has also served in several prestigious visiting positions, including Michigan State University, University of Neuchâtel, Switzerland, 𝗕𝗫𝗄𝗃 Madrid, Max Planck Institute, Dresden, and ICTP Trieste. With an impressive academic output, he has authored around 200 publications in reputed international journals, conference proceedings, and edited volumes. Thank you so much, sir, for joining us. We are truly honored to have you, sir. So please share. Hello, sir. Hello, sir. Hello. Hello, okay, sir. Is there any problem?
Hello, can you see my screen?
Yes, sir.
Is the screen visible?
Yes, sir. The screen is visible.
So shall I start?
Yes, sir.
Okay. Okay, so thank you so much for giving me this opportunity and to present this seminar. This is a topic which is quite interesting in the sense that this is one of the most interesting unsolved problems that we still face. And it's about 40 years now that we have been struggling with this, the understanding of high TC superconductivity. I think most of you know what high TC superconductivity is about. It is superconductivity at very high temperature. By very high, I mean above liquid nitrogen temperature. Typically, I mean, it depends on the system. We'll come to it when we discuss. So the outline of this talk is the discovery, then breaking the liquid nitrogen barrier, basic phenomenology, the phase diagram, the parent compound. It's an antiferromagnetic Mott insulator, the normal state, the doped Mott state and pseudo gap, strange metal overtop regime, and superconducting state, and quantum critical phenomenon. And towards the end, I will discuss on what we agree on and what we do not agree on. So before I get into the details of superconductivity, let me just show you the timeline.
Sir,
Yes.
hello. Sir,
Yes.
sorry for interrupting, but please, sir, make it full screen.
Okay, so is this okay? Is this okay now?
Sir,
Or shall I make it full
actually,
screen? Okay, so let me try.
yes,
Is this
sir.
okay? Okay.
Yes, sir.
So this is the evolution of critical temperature of superconductors, and so till about a few years back, it was discovered in 1986, and till about a few years back, we reached up to about 155 degree Kelvin, and this is under pressure. So the stable superconductors that are above liquid nitrogen, this is the liquid nitrogen line, and these are the ones which are most stable, these two, bismuth strontium and 𝗬𝗂-CU3O7 minus delta. Then there are other kinds of superconductors. I will come back to them. These are the old BCS superconductors, called conventional superconductors. So let me just keep this and show you the bigger picture. So this is this is what I was showing you. There are different classes of superconductors in the high TC, amongst the high TC materials. For example, there are superconductors which are not high TC, and there are these old superconductors, out of which Nb3Ge, Nb3Sn were the intermetallic compounds, and these were the highest TC superconductors till 1986. And then there are these non-copper superconductors, which also are considered high TC, which is above 30 degree Kelvin. And these are barium, potassium bismuth oxide, MgB2, C60 based compounds, and so on. But then the real high TCs, in the sense that which cross the liquid nitrogen temperature, were these copper-based superconductors. So, for example, 𝗬𝗂-CU3O7, HGPA, and a class of compounds. Then recently, about 20 years back, we have these pnictides, FeSe, and there are several others which became superconducting at close to 100 degree Kelvin. And then very recently, there are superconductors that came out of sulfides and hydrides, and these are fairly high temperature superconductors, but they become superconductor at a very high pressure. I'll just come to it. In between, I must mention that there is only one superconductor that came out of India. This was from 𝗕𝗏𝗏𝗏 at 12 degree Kelvin. So this is not really high TC, but this is a borocarbide based superconductor. Now the latest ones, which are around 2019, almost came close to the room temperature in LaH10, lanthanum hydride, but under a very high pressure, 170 GPa. This is extraordinarily high temperature, high pressure, but still the fact that it has become superconductive close to room temperature is really quite interesting. So the target now is to reduce this pressure and bring it down to ambient pressure. there was a report from India of the superconductor at 323 degree Kelvin in nanoparticles of gold and silver, but this is not really, this has not been established yet. Okay, so let me skip this, and this is this lanthanum hydride and similar other compounds, rare earth hydrides, and you can see that these structures are like cages. There is a cage structure, and inside there is this rare earth. So and this is how the resistivity goes. It's pretty close to 250 degree Kelvin, where the superconducting TC sets in. But again, I must tell you that this is at about 170 gigapascal pressure, which is extraordinarily high pressure. So this is the year-wise superconductivity, for example. And these are the old superconductors before till 1970-75. This is Nb3Ge at around 23 degree Kelvin was the highest temperature superconductor. And these are more or less explained by BCS theory. Now the long search for higher TC was actually led by a person from US called Barn Matthias. And he had some advices, which is interesting if you look at it. High symmetry is the best. Peaks in density of states are good. Stay away from oxygen, stay away from magnetism, stay away from insulators, and the last one is stay away from theorists. Unfortunately, this is the route they followed in BCS superconductivity, and he is the leader of that of the people who got the highest TCs in old superconductors. And most of these diktats, for example, are not followed by the high TC superconductors. For example, the high TC superconductors are oxides mostly, and they are pretty close to magnetism. There is an antiferromagnetic state at low doping, and they are insulators in the parent compounds are insulators, and of course this last one I can't comment about. Okay, so this this is the discovery. This was reported by two gentlemen, Alex Muller, the senior person, and his postdoc, George Bednarz. They were at Raajdhani in IBM Zurich laboratory in Switzerland, and they obtained this compound, which they initially could not identify. They knew that it had barium, lanthanum, copper, and oxygen, and they got this resistivity versus temperature curve, where they saw a drop. And then, excuse me, is there any question? Hello? Hello?
Yes, sir. No, sir. No question, sir. Please carry on, sir.
Okay. So then, if you look at it, this there is no Meissner effect reported in this paper, no identification of the superconducting state. See, this is a mix of compounds, X, Y, and so on. They didn't know which one, it's a mixture of compounds. They did not know which compound was superconducting. But they still went ahead and published, and this created a real storm in the community. And then with the help of Takashige, they actually finally obtained the superconducting phase in September 1986. So this is between June and September, they more or less finalized the superconducting state. So the route they followed was interesting. There is something called Jahn-Teller effect, which is, see, most of the old superconductors were mediated superconductivity was mediated by the lattice vibration. And therefore, these gentlemen also thought that a strong lattice vibration, strong coupling to lattice should be a good idea to look for new superconductors. And then, and one of the strongest coupled systems are these systems where you find �𝗕 effect. Now, what happens in this is that the highest occupied level becomes degenerate. Now, if that becomes degenerate, for example, here, in this case, for example, if you have copper 3 plus, in this, take La2CuO4, and this is the structure of the CuO6 octahedron. So the copper is at the center and oxygens are at the peak, at the apexes. And the structure is this, that in this cubic environment, there are the splitting. It's T2G with 3 orbitals from D level. D level has 5 orbitals, out of which 3 come down and 2 go up. So X, Y, Y, Z, ZX are below, and 3Z square minus R square and X square minus Y square are above. Now, if you have 8 electrons, which is this configuration, Cu3 plus, then you have no problem because you put 6 here and 2 in these 2 orbitals, no degeneracy. But if you have 3d9, if you add 1 more electron, then the second electron, the third electron that you are putting in here will go to, what does it go to? Here, X square minus Y square, or 3Z square minus R square. So there is a degeneracy, and this degeneracy is generally lifted by a lattice distortion. So this is the standard structure where there is no distortion, but here you see that there is a distortion along the z-axis, and this elongation along the z-axis brings down the 3Z square minus R square orbital. So X square minus Y square goes up, and the 2 electrons go to 3Z square, and 1 goes to X square minus Y square. So the degeneracy is lifted. So this is an very high, very strong coupling between the lattice and the electronic structure. And this is what they thought is responsible, and this is, indeed, this is there, and this gives rise to the band structure. Which, as I said, we still do not know what causes superconductivity here, but this is certainly one idea that these gentlemen had when they looked for this superconductivity. Now let us look at the normal state of these compounds. For example, one compound which is La2CuO4, you can dope it with barium or strontium. Later on, people doped it with strontium to get a higher Tc. Original paper had barium doping. Basically, you have to dope holes in the system. So if you look at it, the system is after this elongation. I'll show you the structure. This layer becomes CuO2 layer, which is like a plane. So this is like a 2-dimensional layer. So these are called layered superconductors. And you can measure the resistivity along the plane and perpendicular to the plane. So AB plane and C along the C axis. And there is a huge difference between the two. The C axis resistivity is almost like an insulator, and it's very high, whereas the AB plane resistivity becomes there's a superconducting transition here. But the interesting thing here is that this linear behavior. As you can see that the from this point around, it's superconducting. So from x equal to 0.1, superconducting Tc is finite. So you are looking only at the superconducting region, but above Tc. For example, if I come above Tc, you can see the resistivity is perfectly linear and all the way up to about 800 degree Kelvin. Now, this is remarkable. This generally doesn't happen in any material, any metals, for example. The resistivity typically goes as T square at low temperatures and then T to the power 5 and so on at later temperatures. It's strongly temperature dependent, whereas here It's linear in temperature. This was the first huge surprise. And then, of course, there is this anisotropy in resistivity, that rho C by rho AB is a factor of 100, sometimes even 500. The other surprise that came out of these experimental results was the tunneling. And tunneling generally gives you the gap at the superconducting state. And normal, for example, the old BCS superconductors, they have a pronounced gap. You can see that there is no state at this level at around zero energy. So this is the gap. Whereas in high TC superconductor, this was the structure. So you can see that there is no gap, actually. There's a V-shaped density of states. And that means that there is a gap. It is a gapless superconductor. So the gap vanishes at certain directions or certain lines or certain points on the Fermi surface. So in normal superconductors, for example, the Fermi surface is destroyed. You open up a full gap, whereas here the Fermi surface still survives in certain directions. So this is the superconducting structure of these. These are called ceramic superconductors because the material is ceramic. It's a powdery material, and black powders. You can you have to make pellets out of it. They don't come in as single crystals. It's very hard to get single crystals. And this is the parent compound, which is an antiferromagnetic insulator. So let me show you the structure. So this is, for example, the structure. The layer that I was talking about is this. There is a copper at the center. Then there are 4 oxygens in the plane, and then two oxygens at the apex of this octahedron. So these 4 and these 2 make this CuO6 octahedron, out of which CuO2 actually, these 4 oxygens are shared by another copper. So it becomes CuO2 plane. So the initial idea was that the superconductivity is taking place primarily in the CuO2 plane, which is still what people believe. So the CuO2 plane is the one which people actually look into. Now these are 2 different compounds. One is this lanthanum copper oxide, which I just showed. But there is another compound which became even higher, which had a much higher TC. This is the one which actually crossed the liquid nitrogen barrier. TC becomes higher than liquid nitrogen. YBA2CU3O7 minus delta. So this compound, for example, not only has the CuO2 planes, it also has a chain which is CuO. You can see that these 2 green oxygens do not appear in this plane. So this is CuO, whereas this is CuO2 plane, and this is CuO chain. So this particular compound became very important. It is the first one which broke the liquid nitrogen barrier. Then there are others which also did the same, which is this BISCO, bismuth, strontium, calcium, copper oxide, and so on. There are many other compounds now. But nevertheless, the main motif of all these things is this perovskite CuO2 octahedron, this one, and out of which, due to this Jan-Taylor effect, this will go up, this will go down, and you will have the CuO2 plane. This is a much better picture from the side of this CuO2 planes, for example. And this is the CuO chain. This is YBCO compound, and this is the chain. So the general idea is that most of the action, the superconductivity, primarily takes place in these planes, CuO2 planes, and this rest of the material, rest of these regions act as charge reservoir. So if this requires charge, this plane can take charges or leave charges onto these reservoirs. That's the general idea about these superconductors presently. Now the question is, how do you construct a model? So the model is requires a basic motif, which, as I said, is this CuO2 planes. So therefore, you have to look at the structure of this electronic structure of the CuO2 planes. You have to also determine whether there is a electron-phonon coupling there, and so on. So, as I said, you can see that this is the plane, and so in this plane, Cu is 2 plus and oxygen is 2 minus. So oxygen has px and py orbitals, which are occupied, and copper 3d has this x square minus y square is the last orbital that is occupied, that is singly occupied. Therefore, and this x square minus y square orbital has a structure. I mean, it has this, if you look at its structure, it is x square minus y square orbital is a planar orbital. It has no extension along the z direction. And then there are because there is only one electron in that orbital, you have a spin sitting there, spin half electron sitting in that orbital. So you have to consider both these things in order to model. So this is, as I said, is 3D x square minus y square orbital. It has lobes, and this is plus plus. These are minus minus, and then there are these oxygen orbitals which have, this is py, for example, and these are px. So these orbitals. So this copper, if it has to talk to this other copper, it has to talk through the oxygen orbitals. So therefore, you have to determine the band structure where you have to find out how this copper d x square minus y square electron move around via the oxygen. So this is, as I said, this is the 2px and 2py orbitals, which are, this is 2px and this is 2py. So they act as a bridge between two coppers in the plane. So this is the bare bone structure. This is the copper dx square minus y square, and this is the py, and this is px orbitals, py and px, and this is the next copper. So your model then therefore must have the copper dx square minus y square electron going through the px or py orbitals and onto the next copper. And that is how you have this. I mean, superconductivity requires you to have a metal. The normal state must be a metal. So metal requires this electron to move around, and this is the path it has to take, either this way, or along the x direction, this way. This is a better picture, but it's same picture. So then people went ahead and did a band structure calculation, and they found that there is a strong admixture between the copper electron. It's actually better. It turns out it is better to think in terms of, because you are doping holes by doping the strontium or barium, it is better to think in terms of a whole picture. So that copper one electron in the one band, in the dx square minus y square band, I can also think of that band as a half empty, and that empty electron, it could accommodate two electrons, whereas there is only one electron. So therefore, there is a hole in that band, and that hole is found to be propagating. For example, the Hall measurements told us that it's mostly, the carrier is mostly the holes. So therefore, the picture that actually emerged was that this copper hole is moving through the 2px, the oxygen orbitals onto the next copper. And this is the band structure. I will not get into the details of that, but what was suggested was that this famous �𝗲𝗃 singlet, it involves a copper x square minus y square hole, hybridizes with a hole on its neighboring oxygen 2px or 2py orbital, and this singlet that is formed now moves as a composite entity, and the band structure represents the band of these holes, these �𝗲𝗃 singlets. And this is the object that is your so-called quasi-particle. I mean, you in any description of a metal or in solid state systems, you need to understand which one is identify which one is the quasi-particle. And it turns out this �𝗲𝗃 singlet is the quasi-particle in this case. You must realize this is a strongly correlated system because 3D orbitals have a large local Coulomb correlation. And therefore, the picture that I'm telling you so far, single particle picture, is not really the correct picture. You have to think in terms of these composite particles, which is, for example, a �𝗲𝗃 singlet. And this is the quasi-particle that we will discuss. So whenever we say an electron or a hole, basically a hole, we actually mean this �𝗲𝗃 singlet in this compound. So this is just a bit of a recap as to what I said so far. The Bednorz and Mullard started this whole thing. Actually, it was announced in Bangalore in 1986 December. And there was a big conference in Bangalore where this was reported. The highest BCS superconductor was this one with 23.2 degree Kelvin. Then came this 𝗰𝗵𝘂𝗶 in March 1987. People found this group at Texas. They found this 𝗰𝗵𝗂2Cu3O7 compound. If you do holes in that, it becomes superconductor. As I showed, it has very similar CuO2 plane, but then in addition, there is a CuO chain also. And that broke the liquid nitrogen barrier. TC was 77 Kelvin. TC was greater than 77 Kelvin. Actually, it went up to 93 degree Kelvin. Now here is the first phase diagram that came up. So this is the site that we are talking about because we are doping holes by doping strontium. This very narrow region is an antiferromagnet. The parent compound La2CuO4 is an antiferromagnetic insulator. It's considered a Mott insulator. I will come back to it. What is a Mott insulator? It's basically a strongly correlated insulator. And then once you start doping, within about 5%, the system becomes this antiferromagnetism vanishes, the long-range antiferromagnetism vanishes, and then there is a narrow region which is thought to be a spin glass region, where spins are not vanished. Spins still exist, and short-range order exists, but no long-range order. And then there is a superconducting dome, and the superconductivity is highest at around 0.15, 15% doping. This is the region supposed to be normal metal above TC. And here you can see there is a line. This line gives a region. Below this line is a region called a pseudo-gap region. I'll come back to it. It basically says that there is a gap. In the excitation spectrum of the metal, there is a gap-like structure. So if you look at the transport, you will find that there is a gap-like structure. And then there is this normal metal region. Normal is under quote unquote. It's actually a strange metal region where the resistivity does not behave like a normal metal. As I showed, it is extremely linear for a very large temperature range. So there are four main regions: antiferromagnet, then a pseudo gap. And this, as I said, there is a possible spin glass region here. It's a very narrow region. Then there is a superconducting region. And then there is this so-called normal state. And beyond this is called the overtop region, which behaves like which is assumed to behave like a normal metal, which is a Fermi liquid. The description of a normal metal is in terms of Landau-Fermi liquid. And that's what people believe is in this region, but that is recently in doubt. People have found unusual behaviors here also. And this region, as I said, is very unusual. It's now called the strange metal region. Now, later people did many more experiments. The experiment here is really extraordinarily sophisticated. And people found that these regions are not unique in the sense they are not clean pseudo gap, not clean metal, and so on. There are all kinds of orders that are there. So this picture, for example, tells you that there are this nematic, there is, all kinds. Superconductor, then the pseudo gap, and spin gap, then so on and so forth. I mean, this actual phase diagram is extremely complicated. But people generally still focus on those four regions, as I mentioned. This is the antiferromagnet, this is the pseudo gap region. Then people believe that there is a charge ordering takes place here, stripe-like charge ordering. But as I said, there is no consensus on this. And then there is this strange metal, and then there is so-called good metal or Fermi liquid, Landau-Fermi liquid. But then again, this is in doubt now. Okay, then I will not get into this CDW because this is not borne out by later experiments. So, as I said, this is what we will consider. There is a antiferromagnetic insulating region, pseudo gap region, non-Fermi liquid region, which is the strange metal, and there is a metallic region, which is believed to be a normal metal. And then there is a superconductor. But then this superconductor, as I said, is not a gapful superconductor. There is a superconductor with no gaps in certain directions. Now, there are these statements people make, which is probably correct, but again, some people do not believe it. The TC, for example, of say 160 degree or 150 degree, 90 degree is too high for electron-phonon coupling to give rise to such high TCs. So therefore, people were looking for alternative mechanisms. And right from the day one, the idea of non-BCS or non-electron phonon superconductivity was very seriously thought about in these systems. Now, later experiment, once you know that this is a gapless superconductor, you try to understand what is the nature of this superconductor. So as you know, the superconductivity happens due to the condensation of Cooper pairs. Two electrons form a pair, which is called a Cooper pair, and that goes into a condensed state. Now, this composite object, the Cooper pair, is a bosonic object, and bosonic objects must have their total angular momentum even 0 to 0, 1, and so on. So therefore 0, 2, and so on. So therefore, this superconductor, for example, S-wave superconductor, which is the old superconductor, there the spin was 0, and therefore the angular momentum was also 0. So this is that is why it is called the L plus S will be 0, and therefore this is D wave, that is a S wave superconductor, completely isotropic. Whereas if you have a triplet superconductor, for example, superfluid helium, or people consider triplet superconductivity, triplet superfluidity, and there you have the superconductor, the S is equal to 1 for a triplet. Therefore, L was also taken to be 1. So it has to be an even number. Sum has to be even, 0, 2, and so on. So in this case, because we knew from experiments, particularly from NMR and NQR and other experiments, that the spin state is still 0, so it's a singlet superconductor. But then there is and then the choice for the L is 0, 2, and so on. So therefore, 0 is ruled out because 0 will give you fully gapped superconductor like the old superconductors. So people latched on to the idea of L equal to 2 superconductor, where the angular momentum is 2. Therefore, and that has an advantage. That has a structure like this in the momentum space, and that has these regions, as you can see, this is plus, minus, like the dx square minus y square. That is why it is called D wave superconductor. So therefore, such superconductivity has such superconducting wave functions have there are regions of 0. For example, if you have to come from plus to minus, you have to cross through 0. So these are the points, these diagonal points where you have 0. So this is where the gap vanishes at these 4 points. Now, if the Fermi surface is it's a 3-dimensional Fermi surface, so these will become lines if you rotate on a sphere. Okay. So D wave versus S wave, I mean, this is a good picture. This is the old Fermi surface, and these are the lobes of your superconducting wave function, and L equal to 2, and therefore D wave, and therefore you can see that there are these zeros of the wave function, the pair wave function. Whereas in S wave, there is a gap everywhere. It's always the same sign, and there is a gap everywhere. These are called nodes. Like a node in a wave function, here is a superconducting wave function has a node. So therefore, the idea of L equal to 2 or D wave superconductivity took root, and people started doing experiment to check whether there is a L equal to 2 superconductivity. Now, where does it come from? The question is, why should you have, why is it that S wave superconductivity is not happening? The reason, the symmetry allows it, because your spin is 0, total spin is 0. Therefore, you could have S wave superconductor. The orbital part could be L equal to 0, but it is not. There are 2 reasons. One is that we know that from experiments that there are this tunneling experiment told us that there are nodeless regions. Sorry, there are regions where they gapless, there are nodes. And second is that we also know that these copper electrons, they repel each other. Now, if the 2 electrons repel each other strongly, Coulomb repulsion, then it is better to have a wave function which is 0 when 2 electrons come together, come close. So if you have at the same side 2 electrons, the wave function, the pair wave function must vanish, and repulsion requires that. So therefore, you have to have the pair wave function must vanish when r equal to 0. The distance between the 2 electrons is 0, and that is what this thing does. This wave function, if you Fourier transform, this will exactly do that. So the 2 paradigms for superconductivity are now the conventional old superconductor usually occurs in L equal to 0 pairing channel to take advantage of the attractive electron-phonon interaction. Therefore, 2 electrons are close to each other and they can be at the same position, r equal to 0, and avoid Coulomb repulsion in time. So this I will not explain here. This is called a retarded state. And That's what happens in the old superconductivity. They are separated in time, but not in space. The pairs, I mean, the two electrons of a Cooper pair. And now there is this new unconventional pairing, which is, it occurs at higher L pairing channel, even L, for example, here, because S is 0. And thereby you can avoid the Coulomb interaction in real space. Psi, the superconducting wave function, has a node at r equal to 0. So the two electrons avoid each other. So this is L equal to 0 is the S wave and 2 is the D wave. So these are different forms of their irreducible representations. This is the one that I was discussing, is this one, cos kx minus cos ky. The second, dx square minus y square. This is the case space picture. So this is the one that is proposed for this high DC superconductor. And experimentally also, people found that this is probably the most possible structure, the wave function of the superconducting pair. So this was the experiment that actually established it uniquely, more or less convincingly, that we have an order parameter. The superconducting wave function has this kind of structure with the phase going like this, which is consistent with this dx square minus y square. This is a very interesting experiment done by van Haldingen in 1994, and the paper came out in 1995. It's a long paper in Review of Modern Physics. So the tunneling, for example, the experiment that van Haldingen did gave us information about the phi, about the structure. Where is the sign plus, where is minus, how does it go around in a circle? So the signs of the wave function at every point on this circle. Whereas the tunneling experiment did not give us the sign. It only told us that the gap vanishes somewhere on the Fermi surface. So the Fermi surface remains intact somewhere. But this experiment told us where exactly is the gap vanishing. And this turned out to be the correct picture. Now, what is the consequence of this non-trivial pairing? There are now, for example, here, these are the regions where you have a pronounced gap, these plus or minus regions. But here, at this point, you have a zero energy excitation available. So that immediately tells you that the tunneling will become gapless. So you have zero energy excitations available. I mean, let us not get into this. So this is, for example, the density of states now. The density of states will now be have a structure which is like this. If you remember your superconducting density of states, normally they have two peaks, one at minus delta, one at plus delta. But here you will have a non-zero number of states at finite at omega equal to 0. So the consequences are also available, also seen in other experiments that particularly look at the thermodynamics or excitations. For example, your specific heat, for example, specific heat for a free Fermi gas, for example, in a metal, we know that it goes linearly with temperature. Whereas in the nodal superconductor, if you do the same procedure, if you use the same procedure, but use this nodal structure of the superconducting order parameter, then you will see that the C goes as T square. And this is verified by the experiment. This is seen in the experiment. So the low energy quasi-particle states, for example, I mean, you can measure the lambda, and that is in S wave, because of the gap, it's much higher up here, whereas because of the gaplessness, it goes below in D wave superconductor. So all these kinds of experiments were done And they more or less verified that you have a gapless superconductor, but gapless around certain directions, certain nodes. So this is one of the best experiments that people did at that time. This is ARPES, angle resolved photoemission experiment from Stanford, and what they found was that what you can do here is that you can move along a direction in the Brillouin zone, and you can look at the nature of the Fermi surface along these directions. And they found that there is this. So this experiment, for example, it's going, if you go along gamma y direction, you are going through the node. So at some point, when you hit the Fermi surface, your gap must vanish. And that's exactly what happened here. Shown in terms of an angle, but this is where the Fermi surface is, and this is where the node, this node is, where the gap vanishes. And you can then change this direction and figure out all the regions of all the phi's angles, and therefore you can plot as a function of k in the Brillouin zone, and the gap fits very well this particular form, which is the DOF form. So here, for example, are three crucial experiments shown. This is the Van Harlingen's experiment, the exact measurement of the phases. And this is the one where this is called pi junction experiment. I'll not get into the detail, but you can actually tunnel an electron along this metallic ring. And if they have different signs, the matrix element will vanish because they have different signs. Whereas if you add another pi phase through this loop by applying external magnetic field, then you add another sign to it, and then this tunneling becomes possible. So this is called the pi junction experiment. And so the experiment almost unequivocally showed that this is a DOF superconductor. Okay, so this superconducting phase is well understood, and people also measured the coherence length, and the coherence length turned out to be fairly small. Now the question is, for example, by small I mean in normal old superconductors it's about 10,000 angstrom, but here it's about 30 to 50 and maximum 100 angstrom. So it's extremely low. So then people realized, particularly Phil Anderson is the first person who came out with this idea that, look, this is a strongly correlated system, and this strong correlation can lead to a completely different scenario. Now, what is strong correlation? Strong correlation we knew for a long time. In 1937, for example, people already did the band structure of nickel oxide, and they knew that it's a half-filled band, and a half-filled band must be a metal. But then when experiments were done by 𝗕𝗏𝗏, he found that this is a very good insulator actually, and the band gap is about 4 electron volt. Now something which ought to be a metal becomes a semiconductor, becomes an insulator with such a huge gap, was very surprising. In 1937, in the same conference where this was presented, there was Rudolf Parkes who pointed out that this must be happening because the nickel oxide involves electrons in the 3D orbital, and 3D orbital is a very narrow orbital, and in this orbital electron correlation is very strong. The electrons are pretty closely localized, close to the nucleus, and they feel the repulsion. The two electrons of two neighboring sides will feel repulsion when you take one electron to the other side. So therefore, this idea was proposed there, and he said that this will lead to a gap at the Fermi level. And Mott in 1949 came out with a theory for that, he worked out the correlation, the relations. Basically, at what doping level of doping you will find this gap opening up, and he also found out the criterion for this. He predicted there will be a first order transition from a metal to an insulator if you increase the correlation, the Coulomb interaction. So what is this correlation? It's a so kinematic, for example, kinematics and statistics can also produce correlation. We know magnetism is, for example, magnetism comes from Pauli principle, which is a kinematical constant, statistical constraint, and then that statistical constant gives you kinematical constraints. So two electrons of the same quantum numbers cannot come at the same site, and so on and so forth. So these are known. These were already known. For example, in neutron stars, we know that this degeneracy leads to incompressibility. You cannot compress a neutron star further down. This is the famous, Chandrasekhar limit, for example, shows that if you break that, then there is nothing that can stop you. So that's how you calculate Chandrasekhar's limit. So this is the incompressibility of neutron stars that comes of a kinematical or statistical correlation. Coulomb interaction is a very physical interaction. This we know, that two charges of the same sign repel each other, and electrons are all have the same sign, and therefore they will repel each other when you bring two electrons close. So this can be in 3D orbitals, for example. This correlation can become very strong. And when do we call it strong? When the Coulomb correlation, the repulsion, has the same order as the bandwidth. So if the bandwidth is, say, 2 electron volt, and if your Coulomb repulsion is also of the order of 2 electron volt, then we call that you are in the strong correlation regime. And then it is difficult to write the wave function as a product wave function. In quantum mechanics, that's what we do. For single particle wave functions, we construct a many particle wave function by taking a Slater determinant, which is a product of single particle wave functions, suitably antisymmetrized, and that will not work here. Of course, you have to antisymmetrize in a computer, which is, again, you cannot do beyond a few electrons, a few sites. So what does it do? Strong correlation leads to localization. And localization of electrons costs energy, because Heisenberg uncertainty wants electrons to move about. It wants to delocalize electrons. The larger the available space for an electron, the less will be its energy. Whereas here we are localizing electrons by correlation, therefore it costs energy. So therefore, we have two things playing here. One is this statistical correlation, which comes from quantum mechanics, and then Coulomb interaction. Both combined will give you a new state of matter, and which is what Mott showed, is an insulating state, which is called Mott insulator. It's not a band insulator. In band insulator, you have a valence band and a conduction band which are separated, which have a gap in between. But here, the concept of band does not work very well, and you have to have you have to have two regions of electronic states. One will be localized, another will be extended, and these are called lower Hubbard band and upper Hubbard band, and these bands are separated by a Coulomb gap. So these are many body states. This is not a single particle bands. So what to look for? As I said, 3D is the best place to look for. 4F also has strong correlations, but 4F are very strongly localized. And they give rise to heavy fermions. This whole series of heavy fermion physics comes in the 4F. Kondo physics comes in the 4F. But the Mott transition typically happens in the 3D level, 3D, 4D, and so on. So therefore, this is what happens in cuprates, for example. That's what Anderson said. So this normally, as I showed you, that the upper level, 2 levels, because of Jan-Taylor distortion, there is a split. 3 levels come down, and they accommodate 6 electrons. But then you have 3 electrons to be accommodated here, and because of Jan-Taylor distortion, there is a split. And this split gives 2 electrons in the dz square and 1 in the dx square. So this would have given you this picture, that it will be still a metal because there is a zero. You see the band is partially filled, half filled actually. This band, the dx square minus this top level is half filled, and there is only 1 electron instead of 2, and that should have been a metal. But then you put in the Coulomb repulsion, large U, and that band now, that density of states now splits into 2. One is the upper level and this is the lower level, and the lower level now is completely full, and therefore this is an insulator with a gap. So this is the Mott picture. This is called the Mott insulator. And you can also show that at half filling, there is the second order perturbation theory you can do that shows that this will lead to a antiferromagnetic state. So this Mott insulator is not only an insulator, it also has a low energy charge degree of freedom, which is the antiferromagnetic magnons coming out of these magnetic excitations of this antiferromagnet. But now what you are doing is that this antiferromagnet, which is a Mott insulator, you are doping with holes. So you are removing electrons, and that is what leads to superconductivity. So that is the picture that Anderson first proposed. So it's a dope Mott insulator which becomes superconductor. And that model is this model that represents this physics is the simplest possible model is the Hubbard model, which is basically you can think of as electrons or holes hopping from copper side to copper side via the oxygens. And then when they come on the same site, they will have a strong repulsion. And that repulsion is only at a particular site, at every site. So when 2 electrons sit neighboring to each other, there is no repulsion. But that's not actually correct. Coulomb interaction has a longer range, so that repulsion is also there. But that was neglected in this model. Hubbard proposed this model in 1963 for a detailed study of the Mott physics, basically the Mott transition. And this model is one of the most famous model in the history of physics, and this is called the Hubbard model. Hubbard wrote 4 papers on it in 1963 itself. So the model is not defined unless I tell you what are these I and J's. These are sites, and sites means there must be a lattice, and the lattice has to be specified. So it can be a square lattice, it can be a triangular lattice, it can be a hexagonal lattice, and so on. But then in cuprates, we know that the lattice we are talking about is a square lattice because it's this copper oxide plane, CuO2 plane. Okay, so this is a way you can define the Hubbard U. So if you put 1 electron in a D level, then reduce 1 electron from that level and add these 2 energies and subtract from that twice the nth energy level, and that gives you formally U. So this is pictorially, this is what Hubbard model is. You have these spins, electrons, and the electrons want to move, and when they go in such a way, if one side becomes doubly occupied, so each side has 1 electron. This is a single orbital model. So 1 electron, and then when they move, it can happen that 2 electrons come together because that's the maximum you can accommodate in 1 orbital. And these 2 electrons, once they come in the same site, they will have a repulsive interaction of U. And the kinetic energy, when they move, they gain an energy of T. And that's the It's called local Coulomb energy, and it leads to localization because this U is large. So two electrons, if one electron is sitting at a particular site, the other electron will prefer not to come there because it has to pay a lot of energy, U. And then you have to also tell us the dimension of the lattice. Here it is 2 dimension and a square lattice. So that's the complete description. On a square lattice, for example, this is if you have very low densities, this is your Fermi surface, and then if you increase your densities, the Fermi surface expands, and at half filling exactly, you have these blue lines, and the corresponding density of states is this. You can see that there's a huge pile up of density of states at 0 energy. And this is very special for say square lattice, and this leads to a divergence here. This is a logarithmic divergence of density of states at 0 energy. For example, in triangular lattice, there is a divergence, but that divergence is weaker and it is not at 0 energy. And this divergence is often called the Van Hoff singularity. So, okay, so let me not get into, I've already discussed what this is. This half-filled band will split into 2 different density of states, regions of density of states with a gap of the order of U. If U by bandwidth is very large, if U is larger than the bandwidth. Now, in this case, a particle picture, whether it works or not, is a big question. And we know that Landau Fermi liquid, for example, it actually tells us that you can still think of quasi-particles in an interacting system. And that is, it's like this, that pictorially, it looks like a real particle is this. And it creates a dust storm around it when it moves fast. And then this dust basically covers it, and this whole object is now called so this is called a dressing by the dust, for example, and its whole object is called the quasi-particle, quasi-horse, as this cartoon says. So the band structure for a real particle, for a free particle, for example, is just an epsilon naught of k, which is typically k square by 2m, h cross square k square by twice m. Whereas in a quasi-particle situation, in addition to this, you have additional self-energy. This self-energy is k dependent and energy dependent. So this is it's like a particle moving in a liquid. This is particle moving in a gas. In a liquid, you have a much slower motion. The particle is dressed by the other, you have to move other liquid particles around to move. So effective non-interacting description still survives, but you have to pay this additional cost of self-energy. And that's what people actually do. They write down the Green's function, and Green's function produces for you this, if you take care of the interaction, it produces for you a sigma of k omega. I'll not get into all these details, but I'll just show you why you should expect a antiferromagnetic state. For example, that if you have 2 sites, for example, with 1 electron each, which is the half-field limit, then you can see that this electron, when it hops here, there are two ways this thing can happen. Either this electron hops here or the other electron hops back. So these 2 states are possible. But in the intermediate state, which is this, it has a high energy, which is U, because you are paying the U energy here. 2 electrons are on the same side. So it is not stable, it will come back. But the coming back can happen in 2 different ways. You started from here, you can come back in a different way, in the same way, with up here and down here, or you can go down here and up here. So from here to here, there are two different ways you can come. And this is like an antiferromagnetic. This is an exchange of spin. The second one, for example, is an exchange of spin, and the first one is not an exchange. It remains the same. Now, if you remember your Heisenberg model has these two terms. One is that Sz.Sz, and the other term is S plus S minus. And this is exactly what this is. And this process, actually, in second order perturbation, this process, if you start from here, the process leads to this exchange plus the diagonal term, Sz plus S plus S minus. So that is the Heisenberg model. So effective model from here to here is actually Heisenberg exchange. And that is the reason you have an antiferromagnetic state which is stable compared to, for example, a ferromagnetic state. If I had a ferromagnetic state here, this electron would not move at all. Okay, so I don't know how much time do I have, Dr. Ipshita?
Sir, 15 minutes.
So should I keep it for discussion, or I will continue?
Sir, you can share for 5 to 10 minutes. Then for 5 minutes, we will keep for discussion.
Okay. Now, in 1970, the Gutzwiller actually proposed a beautiful way of looking at this problem. And he proposed a wave function. As I said, that single particle wave functions will not do. So therefore, he proposed that the many body wave function for this situation, this model, Hubbard model, is he proposed this wave function. This is obviously not the right wave function. It will, if you put it in Hubbard model, it is not an it will not get an eigenvalue out of it. So this is not an eigenvector. But then you can't find an eigenvector in a correlated model. Remember, why can't you do it? See, if you look at this model, there is a term which is, take this term, the second term. The first term you can diagonalize, easily diagonalize, and you can, this is just the kinetic energy, and you can always diagonalize a term which has two fermions. These are the fermion creation and annihilation operators. So if you have such two fermionic operators, you can always diagonalize that problem. Whereas this Ni requires two C operators, Ci dagger Ci. This Ni also requires two C operators, Ci dagger Ci. So this is a 4 fermion operator. A 4 fermion operator cannot be diagonalized. So that's the reason it becomes a many body problem. The single body solutions won't work. This part is the single body, this part is the many body. And therefore, you have to either diagonalize it on a computer, and then you cannot diagonalize in a large system, because 4 by 4 is one of the maximum that you can do. The Hilbert space becomes huge. You know, for example, in lithium hydride, people did this calculation for just to get the atomic levels, just as you do it in hydrogen. And the matrix dimension of that correlated problem, Coulomb problem with Coulomb interaction, is already 22 billion by 22 billion is the dimension of the matrix. So here it will be even bigger if you take a larger lattice. So that is just not possible. So therefore, people try to approximate, try to guess. And this is one original idea that came from Gutzwiller. He wrote down a wave function which is like this. So let us see what this wave function. See, this wave function is creating pairs with a probability of 1 minus g on the Fermi level, on the Fermi state, basically the degenerate Fermi surface. So if you g equal to 1, then this is 0. That means there is no correlation between particles. It's just a normal, usual product state of the Fermi C. Whereas if you have g less than 1, then this is finite, and therefore you are basically taking out all the sites which are doubly occupied with a probability 1 minus g. And that's the wave function that he wrote. There is a product here, pi over this. So this wave function is called Gschuler wave function. And this Brinkman and Rice showed that this wave function gives a scenario which actually leads to a Mott transition. There's a gap in the spectrum, and it goes continuously to 0. This Z is basically this. Remember your Fermi function. The Fermi function is for a free fermion is like this. It's a delta function. It's a step function. Goes down from 1. It goes down to 0 at the Fermi level. Whereas here, it basically reduces from there, and there are finite states here. So there are finite excitations here, but then still there is a gap. There is a jump, and this jump is this Z. And when the jump vanishes, Z equal to 0, then you have a completely insulating state. So that was the picture of Gschuler, that you actually slowly go down. And the bottom one is a DMFT picture, which will not get into, but it actually gave you a transition. But then this thing, the picture gave you a gap, gave you a metal insulated transition, but it is not correct. Because this picture rules out all the doubly occupied sites with a certain probability. Whereas we know that there must be the doubly occupied sites, it vanishes at UC, it becomes 0 at the transition. If you look at this formula that you get from here, this is 0. So this is not correct. Even if u equal to infinity, close to infinity, very large, you will always have of the order of T square by U square number of doubly occupied sites. It simply comes from second order perturbation theory. So the fact that you have is D equal to 0 at finite u means that the theory is not correct. And people went ahead and did corrections to this, did perturbation theory, then all kinds of things have been done. The most successful approximation that we have so far is called the dynamical mean field theory, which is basically a theory which is exact in infinite dimension. What it does is that it replaces it. Actually, you can show that this model can be replaced by a completely local model, but keeping all the temporal fluctuations. By temporal fluctuations, I mean the energy fluctuations or time fluctuations in time. So you can actually map this model onto a model which is absolutely local, purely local, but with keeping all the frequency fluctuations, energy fluctuations. And that is kind of a Kondo model. An effective Kondo model is, or Anderson impurity model, better to say Anderson impurity model. And that mapping has been done, and that mapping has to be done numerically. Unfortunately, that is the problem, numerically and self-consistently. And that requires a huge amount of computational effort. And then, of course, since you are neglecting the spatial fluctuations, you will miss something. And people have improved it. There are cluster approximations and so on of the dynamical mean field theory, which can find can do better than that. But it's still an approximation. It is exact only in D equal to infinite dimension. But that is a very promising route, and that has seen fair amount of success. But then, as in all correlated systems, there will always be problems in it unless you can exactly solve it, which is almost impossible as it seems now. Don't know what happens in future, but at the moment we are nowhere close to a solution of this model, such a simple model like Hubbard model. Okay, so I'll skip all these things. So then people actually studied in this D equal to infinity limit. People studied in the dynamical mean field theory, people studied superconductivity in the repulsive Hubbard model. And people claim that they find the D wave singlet superconductor. And there are other claims also. This is called the RVB superconductor. It's the original suggestion of P.W. Anderson. And people have actually showed that you can construct a Gschuler projected RVB superconducting solution in this Wheeler protected superconducting solution, which gives you the RVV superconductor. And these are things I will not get into the details of the theory. This field is more or less still led by experiments, and newer experiments are coming every day. So I think I will stop here, and I will see if you have any questions, then I can try to answer. So it's a long journey. A lot is known, but even more is unknown. Thank you so much.
Any questions for sir, dear participants?
This is considered the most functional of the materials that we have, but unfortunately we cannot still use its functionalities.
Okay. Please, if you have any questions, please ask. Any
I
questions,
think there are no
please?
more questions. Yeah.
Yes, sir. So, thank you so much. Thank you so much, sir, for
Thank you.
delivering
Thank you
such
so much. Yeah.
for delivering such an insightful and engaging session. We truly appreciate the time and effort you have devoted to sharing your knowledge with us. On behalf of Dr. 𝗕𝗫𝗪 and myself, Dr. 𝗕𝗪𝗙 𝗔𝗟, we extend our sincere gratitude and wish you continued success in your academic and professional endeavors, and looking forward to host you again, sir. Thank you so much.
Thank you so much. Thank you. Thank you.
Good evening, dear participant. Good evening. We will have one more session from 5 to 6:30. Then we'll go for validated session, and we need a photo. Please switch on your video so that we can take a group photo. After that, the exam will start from 7:15 onwards. 7:15 onwards, it is for 1 hour, and 20 carries 25 questions, and each question carries 2 marks. So kindly give the exam from 7:15 onwards, and give feedback in your portal. Okay, no separate feedback link will be given to you. You need to log in through your user ID and the password in 𝗕𝗫𝗄𝗏 Academy, and go to the feedback tab and give feedback. Then you can download your certificate. Okay, one more session will start soon, very soon. At 5 o'clock we will start. Thank you.
Sushant sir, are you there? College.
Yes. Please, participant, can you do your video one?
Showing only twisted.
We'll start our next session now. पक्का हो कॉल करेंगे कॉल कर लोगे
दिया दिया பின்னாடி 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 ஸ்கிரீன் தடவிட்டு ஜெல்லி போட்டுமா பலூன் வாங்குனீங்களா எத்தனை பலூன் ஒண்ணுன்னா ஓபன் பண்ணலாம்ல
Very good evening. Is it audible? Dr. 𝗕𝗧𝗔𝗟, it is audible?
Yes, sir.
Yes, sir. Audible, sir.
Yes, sir, audible. Sir, namaste.
Okay. Namaste, namaste. So, Sri and 𝗕𝗧𝗔𝗟, you are disturbing me 24/7. Thanks a lot for your energy and your tempo. Fine. Yeah.
Yes, sir.
Yes, sir. So thank you so much for joining us,
you.
sir.
We need much more
Yes.
such type of program. You should continue with your spirit, your energy, everything. Okay. On that day, I was
Thank you,
driving the day one when we inaugurated. That's why my video was off, and I have told you something on that day. So,
Okay, sir, no problem. Let madam.
Okay. So, sir, welcome you. Also, we both Dr. 𝗕𝗧𝗔𝗟 and myself, Dr. 𝗕𝗧𝗔𝗟, we welcome you to the 6th day of Atal Online FTP named FSFM 2025. So this is our 13th session, and so let me short introduction of yours to our participants. So dear participants, for the 13th session, we have Dr. 𝗕𝗪𝗓 Tripathi with us, who is presently working as the Dean of School of Design and Postgraduate Studies in KIIT University, Bhubaneswar, Odisha. He completed his PhD from the Department of Industrial Engineering and Management from IIT Kharagpur. He has published more than 100 papers in Scopus indexed high-repute international journals, 10 book chapters. He has served as the reviewers and of several reputed international journals. He has received Best Researcher Award in Institute of Engineers and multiple events. He is currently serving as the Chief Editor of International Journal of Research in Mechanical Engineering and Technology, IJRMET, and editorial board member of 6 reputed international journals. Presently, he is working in the various areas of industrial engineering areas. So thank you so much for having us, sir. Sir, please share your screen.
yeah, is it audible?
Yes, sir, audible.
Audible? Okay. So thank you, the two organizers, Dr. 𝗕𝗧𝗔𝗟 and Dr. Sustri Priyadarshini, and I'm very much giving my heartfelt thanks to them for giving me opportunity in your very mega event of the 𝗕𝗵𝘂𝗵𝗵, and welcome all the researchers and the participants. Okay, I hope if you learn something, then that will be a millionaire gift for me. Okay, so let me tell you, today my topic is slightly unique. That is the digitalization in manufacturing. So digitalization in manufacturing is basically what you can say. It is the fourth industry 4.0 revolution, where already there is four. Already we are reached in the industry 5.0. Actually, 1.0 started with the steam engine when you have started the mechanized revolution using from early this 18th century to early of the 19th century. Then after that, we felt, it's very costly to produce the product using some mechanized way. But we have started industry 2.0 from the 19th century with the industry 2.0, that is mass production, standardized product, and the cost will be less. After that, when we have entered to the competitive market, essentials for the IT and electronics, so that automation, we entered to industry 3.0 to the automation area. Then the current era, in the recent era, we realized the industry 4.0, that is the connectivity, means the smart technologies, cloud computing, big data, digital twins, network meshes, all these things. So now already industry 5.0, human context, how the machine-human relationship we have developed, resilience, all these things we are entering now. So today my topic is basically digitalization of manufacturing, where two things I'll tell you. What is the motivation behind that with the introduction? Why it has motivated us. Second part, I will teach you a very interesting tool. In future, any department students can write a nice research paper using that tool. The tool is interpretive structural modeling, ISM. So now I'm sharing my PPT now. Just a minute. Just a minute. Yeah, is it visible to all of you? Is it visible? Hello?
Yes, sir. Hello. It is visible, sir.
Yes.
Visible, sir.
Okay. Should I start now? Okay.
Yes.
So
Sir. Okay.
my topic is digitalization in manufacturing industries. That is an ISM approach. And it is already I have told you why the plan of presentation I have categorized in this way. The basic introduction I'll tell you. Then regarding this area, what are the literature I have extracted from the past authors, I'll show you. Then a nice methodology I'll put in front of you, that is ISM. Then the result and discussion. Then I'll go for the concluding remark. So why digitalization is essential for the manufacturer? Basically, the digital tools. Already I have told you, industry 3.0, automation came. But artificial intelligence, data analytics, all these things, optimize the production processes. Optimize means for any operation, any manufacturing, we have to optimize our resources, 4 M's: man, machine, material, and money. If we can reduce that, it's a great achievement. So which reduces the manual errors, minimize the time, and increase the overall equipment effectiveness. That is the first one. Second one, cost reduction. Obviously, Whenever we are doing something new area, when entering or inserting any new technique, the real-time monitoring and the predictive maintenance help prevent breakdowns, reduce waste, lower energy consumption, and optimize the inventory, significantly cutting the operational cost. Here what predictive maintenance means? The production is going on, simultaneously your maintenance is going on. Like all the public sector, if you go to NALCO, in the industry, you will find during their process idle time, they are converting the internal setup to the external setup. That is the magic of the just-in-time. So if we go with the predictive maintenance, previously what we are doing? We are doing breakdown maintenance. After the breakdown, we are entering into the maintenance area. So if we use the real-time monitoring and with the preventive maintenance, so that energy consumption will be low, inventory cost, the spare parts inventory will be low, so the cost will be obviously optimized. Then enhanced quality and consistency, third one. So digital quality control system, sensors, vision-equipped inspections ensure consistent product quality, early defect detection, and better process control. Actually, what we are doing, why I have mentioned this? Previously, we are producing the product. Then we are sending to the quality control department. They are using some SQC, statistical quality control technique, X chart, R chart, P chart, C chart, different tools are there. Again, or they are having own department. Only they will give the remark. Suppose you have produced X or 100 pieces. So out of 100, 15 or 16 are out of control. They have defective. They cannot enter to the market. But for that 16 means material you have already lost. Energy, workers' payment, so totally cost. Nowadays, when we are starting the production, from the starting point, we have started checking the parameters so that continuously we are improving the quality every step. In the education system also, what we are doing, still now most of the organizations they are doing. The teacher is taking the classes 30-40 sessions. After that, they are giving one page or online, they are telling you give the feedback. The students, so obviously they will write, the teacher is not up to that mark. What he was teaching, it was not, it was bouncing. But after 40 hours, teacher has lost. The students are going to appear the exam next day. You see, total wastage is there. So that's why the digital control system, the sensors, vision inspection ensure that you are checking the quality from the inception stage so that the better process control is there. Then, data-driven decision making, fourth one, who is using this parameter, tick mark, all these things, okay? Don't use that, please. Please. So, Satyam Yadav, don't do that. Okay, so data-driven area, you see the collection of large volumes of data, allowing the managers to make faster, more accurate, evidence-based decisions. Like artificial neural network previously. Now we have entered to the digital new area in the AI. What they are doing, number of causes, what are the different regions, what are the solutions we have kept in one data center. So whenever we are facing any problem, within a second, it will give you the solution. That is the uniqueness of the AI. So flexibility and mass customization. Smart manufacturing systems support quick changeovers and customized production, helping industries respond rapidly to changing the customer demands. Rapidly, you see. And here, the good thing is, mass customization and general customization is what? Customization means when the customer will place a typical order, it is based on one customer. It will take much more time. The cost will be more. But the product will be less. The production will be less. That is the customized job production. Okay. Simply. When the FMS came, flexible manufacturing system entered, they have taken the mass customization, different customers' data will put in a system. As per that, the machine will get the information from our system. Similarly, predictive maintenance, already have told you, asset management. So IoT enabled that sensor will pick up the predictive failure before they occur and extending the equipment life and reducing the unplanned stoppages. Unplanned, like the breakdown, stoppages will be more, idle time will be more. So the predictive maintenance will be there, and IoT, Internet of Things, will sense that after 2 hours, this will here you will face this problem. In the logistic area also, IoT is giving a very good result, very good features. In that case, please don't use these things, you see. So, unplanned stoppages. So, you can reduce the idle time, so my production completion time will be very less. Then why digitalization? We are continuing with that supply chain integration and transparency. Actually, we have realized when we realize this case, please mute all the participants, please mute. It's my sincere request. It's my sincere request, please, all the participants should mute so that everyone will get benefited. So supply chain integration means digital platforms enables the real-time coordination with the suppliers and customers so that improve the demand forecasting, error will be less. So accuracy will be more. Inventory management just in time, which day you need exactly, that is the Japanese concept of the Toyota lean manufacturing, where the inventory is virtually zero inventory and the performance, delivery performance will be super. Then workforce empowerment and safety. Obviously, the digitalization will be there, digital twins, simulations, and the augmented reality. That workplace safety through the monitoring system. Obviously, because manpower is the key resources for us, for any industry. What is the Industry 5.0 has emphasized that. Next, after the 4.0. So sustainability and energy efficiency, number 9. It has told the resource utilization, efficient resource utilization, reduce the carbon emissions, compliance with the environmental regulation, key for the sustainable manufacturing. So carbon trading, we are selling this cap to other industries, the developed countries. We are getting simply money because our productivity is very low. In that case, what we are doing, sustainability is also a challenge nowadays. Any sustainability, environmental sustainability. If you go to the marine, you will go to the e-waste management. Everywhere, the sustainability is a crucial issue. Then global competitiveness, Industry 4.0. So digitalization is the backbone of Industry 4.0, enabling the manufacturers to stay competitive in global markets through innovation, speed, and quality. Obviously, you are creative, and the innovation, both. Creative is the soul and innovation is the heart. And your commercial thing, the industry, is totally the engine. The body is your engine, totally body. So your soul and heart. If your soul with the creative way in the industry, then your heart is the innovation which will drive the industry in a very perfect way. Now, the question why this topic has motivated in basically for the mechanical. For any people, why this topic has motivated? Because COVID-19 pandemic hit the manufacturer in an extraordinary and unexpected way. And the ongoing breakdown has put a whole lot of stress on the manufacturing industry to increase their sales, which contributes 20% of the GDP. You see, COVID-19 actually we came to know that digitalization, we realized that digitalization is very, very essential because I am talking to the Indian context, not the developed countries. Labor constraints, lack of materials and machinery, transportation constraints, supply chain disruptions totally disturbed, unavailability of the buyers, there is no buyers in the market. These are the key obstacles, key constraints, obstacles, barriers, okay, nowadays. Because I have collected everything from the literature. First one from the Ariel et al. 2020. Second one is the Happy and New Year 2020. Similarly, to recover from this situation, artificial intelligence will be a strong vaccine, a strong antibiotic for the manufacturing industries in coming days. Was Montrello 2020, he has told in his article. He has told AI is a strong vaccine for the manufacturing industries. Why? What is AI then? So artificial intelligence market in the manufacturing industry reports covers the size, trends, and industry analysis. Obviously, we are always on one side of the AI. We don't know the coefficient, the viability, the trends, and the size analysis. We are AI means we know only the 𝗕𝗏. But the another side, if you see what the solution you are getting within a fraction of a second, a cancer, early detection of the cancer, early stages of the dementia, the stroke, the health, the heart stroke, the timing of the fraction of second, it has the artificial intelligence had reduced. Another fraction, I'm telling you. So then production planning control, preventive maintenance, and machine inspection are the some of the applications which solved by the artificial intelligence in today's era. One author told Bartik et al. 2028. So planning, quality control, preventive maintenance is also the crucial factors which is solved by the AI. AI-driven machines are a suitable fit to the producing technique, very less fees, not like that. They allow the automation of the task. Obviously, we need the automation as per the market demand, the mass customization. Enhance the manufacturing efficiency and bring system interaction towards human interaction. System interaction towards the human interaction. That is the Yanning et al. And Montreal also. So obviously now 5.0 is emphasizing all these areas now. So this is the totally the towards the human interaction. If I am not satisfied with the performance quality or the report of anything, I can check with the different alternatives, with the different criteria, which will give the accurate result. Now, with this background, I'm going to the second part of my presentation, which is very, very vital for you. If you have the, please, pen and paper, you can note it down. I'll teach you today a nice technique how I have solved these AI factors into a nice different model. Okay, now, we'll start now. What is ISM? ISM is an interpretive structural model. It's a multi-criteria decision making. Different criteria are there. We don't know their relationship. We don't know what is the long-term and short-term goal. We don't know there is precedence relationship. That is the outcome. That will be the output of this ISM model. So this ISM is an interactive and interpretive model in that group's judgment decides whether and how items are related. It is basically based on jury, industry experts, or their opinion, their qualitative opinion, again converted into the quantitative part. And that I will show you, don't worry, wait. So ISM is a structural, it's a totally a structural model-based diagram because an overall structure is extracted from the relationship of the complex set of items and it portrays the specific relationship and overall structure in a diagram model. We'll get some of the factors through the literature review. Then we'll go with the first input from the jury opinion from the judges. Those have been the very good experience in that area, qualitative opinion. Then we'll convert into a quantitative scale using a new technique who has developed that. I'll tell you the 𝗕𝗏&𝗛, the interpretive structural modeling. So ISM methodology helps improve to impose the order and direction on the complexity of the relationship among the elements of the system. Says 1977, he has developed first what is the direction, what is the order, which order, so that we will discuss step by step. So I said, in a nutshell, in a summary, a map of complex relationship between many factors. Please remember, number one. Number two, based on expert opinion. Suppose I want to go with the E-West or the Marine West or anything. I need minimum 10 years of experience, consultants, okay? 10 years experience of the consultant, minimum in that area, so that I can get the right input from them. Otherwise, my model will not be consistent. Third one, determine the long-term and short-term focus factors. The model says, when you develop the model, you will find that which area we have to emphasize just now, that is the short term, and which we finally achieve in a long run. That is the long-term focus. Then finally, classification of the factors into driver, dependence, autonomous, and linkage category. Then finally, what we'll do, we have to classify in this model into all the factors into 4 categories. That is the linkage, autonomous, your drivers, and dependence. Driver means who will drive the other factors. Dependence means which is dependent on others. Dependent means they are in the top of the model, and drivers in the bottom level of the model. Now we'll start. From the literature review part, you see, on the left side, these are the authors. In the this side, these are the authors, okay? These are the authors, the left side. And they have mentioned, suppose artificial intelligence, IoT, big data and analysis, Bartik, Montrello, Yanning, Alam, Singh, Ting, all these, they have emphasized this issue in their article, in their paper. Similarly, Carvalho is told regarding the revenue generation. Kumar et al. And Hivia, they have told the labor constants. These are the areas. Rani also and Singh, they told lack of raw materials and machinery. Simpson, they have told unawareness of the people regarding the COVID-19, because when COVID-19 came, unawareness, nobody knows what is the COVID-19, what to do. There is a fear psychosis developed. Nobody enters into outside. No buyers available, no suppliers available, no drivers available, no materials available. Everything has stopped. Then Moser told process automation. That is also the very, very vital factors affecting the manufacturing industries. Then Bartik Montrello told centralized decision making at the time, 2020, you see, particularly in that time, I have written this paper for the 𝗕𝗵𝘂𝗶𝗿, transport economics, okay? Very good impact factor. So in that case, you see, they have mentioned here, but centralized decision making. If centralized decision making will be there, all the departments will be benefited at. Then Gray, Javed, all they have told transportation constraints, barriers is a crucial issue. Manufacturing industries, they have faced the real scenario. Sarkis told just-in-time and lean production. Just-in-time means when the customer, my consumers needed, I need the product today. Today we will manufacture, and today my supplier also supply the material to me. So my raw material inventory virtually zero, my finished inventory virtually zero, because today I will produce, today he will supply, today I will produce, today I will send to the consumers. You see, so it is a just-in-time. Lean production means where the wastage is zero. That is the lean production. Similarly, Ivanov told supply chain disruptions. If manufacturing industry depends upon, if the supply chain will not be disturbed, then system will continue. The small element, suppose there are number of suppliers, okay, to my industry, number of suppliers. There is a number of suppliers are there with me, okay? So that you can think, okay, suppose one supplier, okay, if I miss a small component, my whole assembly cannot be possible. Just to think about automobile, a small chips. Suppose all during that period, you see SUV 700, that, and any vehicle, the four-wheeler, those are using a small chips even. Due to that, the waiting time was more than 1 year. So this is the basic thing, the supply chain disruptions. So supply chain once disturbed means the whole system will be in the chaos situation. Unavailability of the buyers. No buyers ready to purchase at that time because product was not there, and the buyers also confused what to do. Then product diversification. Most of the industries, they have diversified. If they will not diversify, they cannot sustain in the market. So product diversification. These are the factors we extracted from the past authors' literature. Then we will develop the model. Okay. Now, the summary of the literature, review for the literature says, on the basis of these reported studies, one may conclude that there is not a single list of factors that all are applicable in all the industries, because my steel industries, the factors are different. Pharma industries, the factors are different. Textile is totally different. In other words, each industry can have a few factors that are distinctly from those of other industries. Obviously, some factors may be common, or some factors may be different. So such uniqueness of factors relevant to a particular country can be attributed to the fact that major difference exists in these countries, because country to country also develop the different. Why? Because cultural setting. What the cultural setting in India, that is not in the South Korea, that is not in the Singapore, that is not in the Japan. Similarly, skill level of workforce. Our skill capability of the workforce is different country to country. Availability of the venture capital. How much we are spending our R&D? Very, very less. It is less than 1%. Now 1.6% of our total budget. The other country, like developed countries, around 37% of their budget is R&D. So where we get the creative scientist, Nobel writer in the different innovative field? Technological capability, obviously, if R&D and technological capability will be low in like a developing country like us, obviously, then R&D management strategy. Our strategy is also different, and other country, other industry also there is different. So because there is a difference in the cultural setting, workforce level, your venture capital, these are the technological capability, R&D mission, vision. So it is, you can say, manufacturing base of any country, either it is a direct outcome technology transfer from abroad or technology developed within, or largely determines the extent of the R&D practices in that industry. So factors may vary from one industry to another. What the manufacturing industries we are doing? Either we are importing the technique from outside. After the COVID, our Honorable Finance Minister Sitaramanji, Make in India concept we have started. At that time, online also, no Dell, no HP laptop, nothing is available. Then Make in India concept, the design changed, then we have changed the design, then production has taken another 6 to 7 months, okay? Then we have changed to the scenery. So that, because our everything, because we are dependent only from one other countries, other suppliers, we don't know what is the actual source of the supplier, because one supplier was supplying the material from last 30 years. I have industry here, but I have never asked any other materials available with you. Now the concept they have changed, the offshoring to reshoring. we are getting one material component for our industry from Germany. Once COVID-19 has taught a lesson to us, very nice lesson we have learned from them. No, we have to find out nearby Asia Pacific region, any other alternative materials are there or not. So that as per that, we have our design will be changed. So our product is completely different. Now see. So the critical finding of this research issue came, identify the factors affecting the manufacturing industries during the COVID-19 and what are the relationship among the identified factors. Then we will realize what are the relationship among them. COVID-19, what are the factors? Please identify, already have identified those factors in the literature review, in the bold letters I have shown you. Then what is the relationship that identified factors? So my research objective came here today is to develop a structural model of factors affecting the manufacturing industries during COVID-19 and determining their driving power and dependencies. So factors, already we have listed some factors. Okay. Now we'll tell them, we'll develop a structural model where we'll find out which factors are driving other factors or which factors are dependent on others. That is the basic objective of today's session. Now, this is my framework of these research issues today. So identification of the critical factors affecting the manufacturing industries during COVID-19. For that, I have used the ISM, interpretive structural modeling. Okay, that is the step there. Okay, and these are the techniques. Now, I'll tell you one by one step here. Pairwise relationship, reachability matrix, label partitioning, classification, autonomous dependent linkage and drivers, derive the structural multi-level the diagram, then strategic analysis. How we got this relationship? Using the expert opinion. The jury members say expert opinion. So with the expert opinion, we'll get it. But in the critical review literature, we got these 12 factors. Already I have discussed with you. Significance of AI, unawareness of the people regarding COVID-19, labor constraints, process automation, revenue generation, lack of raw material and machineries, centralized decision making, transportation constraints, just-in-time and lean production, supply chain disruptions, product diversification, and unavailability of the buyers. So these are the 12 factors already we have extracted. Okay. That now we'll find out how the relationship will develop, which one out of these 12 factors, which one will be my bottom level drivers, which are my top level are the dependent factors, which are autonomous linkage. I will discuss now step by step. So now, very, very important session I'm going to start. Any researchers are there? If you want to write any paper for the very good journal like 𝗕𝗧𝗔𝗍 Scopus, then you can your pen and paper, note down everything. Okay, I'll tell you what to do now. So, first step of the ISM methodology, structural self-interaction matrix. I'll go very slowly. If any doubt also, you can write, you can contact with me, don't worry. Here, what we'll do, it is the first step of the artificial intelligence area or the digitalization area that I have collected the data from the experts. From the experts, those are in the different industries. From where we have collected? Very few industries in India, they were using the digitalization at that time. Some automobile ancillaries, Chennai, some pharma industries, they were using this. Okay, we have collected the data. And there is a pairwise relationship, 12 factors we have taken. We have told them only 4 things. So it is influencing another one or vice versa. X and Y, two factors, suppose there is a relationship, I will ask. X is influencing Y, yeah, Y is influencing X. And one more relationship will come. No, sir, both are influencing each other. Both are influencing each other. Or last option, there is no relationship between these two factors. So four areas, four symbols I am using here, that is V, A, X and O. Bhakso. What is the relationship? If parameter I will lead to parameter J. If two variables are there, two factors are there, if you will ask to export, I is influencing J, yeah, just vice versa, J is influencing I. If I is influencing J, then the symbol will be V. Okay. If J will lead to parameter I, then it will be A. If both are lead to each other, then it will be X. And O means if there is no relationship, I and J, it is unrelated or there is no relationship. So the SSIM has developed. So SSIM developed. Now see the SSIM now. Very interesting. You see. Significance of AI. The short term we have used in the researcher. We have here. SAI means significance of AI. On awareness of the people, COVID-19, UPC. Labor constants, LC. Process automation, PA. Similarly, on availability of the buyers is UB. Product diversion, PD. Supply chain disruptions, SCD. Just-in-time, lean, JIT. Transportation constraints, TC. Centralized decision making, CDM. Lack of materials and machines, LM. And revenue generation is RG. Now we have asked this very simple question, you see. Significance of AI, and one is on awareness of the people. UPC means on awareness of the people during COVID-19. Significance of AI is influencing on awareness of people COVID-19, or due to the unawareness of the COVID-19, okay, it has forced us कि चलो implement किया जाए AI. 11 experts at that time we have taken, perhaps in that paper you will find it there. Most of the experts has agreed, no, because no buyers, no people, unawareness of the people, because regarding this, so we need the substitute of the workers, all these things. If AI, that forced us, okay, chalo, you have to go for the significance of AI is essential. That's why J is influencing I, so it is just A. Suppose significance of AI to PA, process automation. Obviously, if AI will be there, it leads to process automation. Because I influencing J. Suppose one is O. O means there is no relationship between two variables. On awareness of the people with the labor constants. On awareness of people with the labor, there is no relationship. On awareness of people and labor. Labor is not available during that because there is a fear psychosis, it's the COVID-19 something. But on awareness, you see, it is how it is related. So if there is no relationship, then it is the, you can say, then there is the symbol you will use O. Suppose X, where is any X is there? Yes, you see. Here there is a term X. X means if both are related, both variables here, two factors are related. What is just-in-time production and lean production to, product diversification. Diversify the product. If you are going with the just-in-time, which day is the same day, suppose new product want to be launched tomorrow, the same day the supplier will supply, you can produce. So both are product diversification leads to this, and just in time, that also leads to product diversification. Any other X? Yeah, here another X is also here, you see. Process automation and the centralized decision making. If the process automation will be there, that influencing the centralized decision making, and centralized decision making is there also, it leads to the process automation, automatically the process. So first step is SSIM, structural self-interaction matrix, which will be collected. It is the input of my research. It has, now you will ask me, half of the whole matrix, you have shown half, other half why it is blank. That will be the mirror. I'll go to the next step. I'll tell you. Obviously, that will be a reflection will come, like a correlation matrix. Doing that, the relationship that will give a reflection. What you have shown here, you see all these things. The result automatically will, it is the half of the things you are getting. Other things automatically, next step, you will get. How? Next step known as the reachability matrix. First step is over. SSIM. You have to use 4 symbols. V, A, X, and O. So B means it is A is influencing B. A means if B is influencing A, vice versa. And A, B are both are related to each other, that is X. And A, B are not related to each other, no relationship, that is O. Now, after this, you will convert into the binary matrix, means 0 and 1. Slowly, I am coming to the qualitative to the quantitative area now. So, second step, the tool is known as the reachability matrix. What? Reachability matrix says your one is these things. Suppose you have to put 1 and 0 everywhere, 1 or 0. If it is A in the row, that will be, you will use 0. If V in the row, then it will be 1. A is 0 in the row. Okay. But in the column wise, it will be different. Just it will be 1 in the column wise 1. Then it is 0 here, again 1. V is here 1, it will be 0. Then A it is 0, here it is 1. Just opposite. V means here 1, it will be 0. Then here it is 0, 1, 0, 1 and 0. Just opposite. But if it is X, then 1, 1 is case. In this case, you have to put 1 here. This process automation to CDM and CDM to process automation. CDM to process automation. Here also we'll put 1. So all these area you will fill it off now. All the area. Because diagonally 1, 1, 1, 1. Big factor to same factor, transitivity is there. Your relationship with U is always 1. Okay. That is the transitivity. Similarly, you will see the very good feature of the reachability matrix. Now, SSIM has been converted into the binary matrix. The reachability matrix substituting V, A, X, and O by 1 and 0. The whole substitution of the 1 and 0. If IJ entry in the SSIM V, you see what I am telling you. V, IJ entry in the reachability matrix is 1. IJ entry SSIM is V. Then reachability matrix it is 1. But column wise it is 0. Similarly, if IJ entry is A, in the row wise it is 0. But column wise it is 1. If IJ entry X, then both reachability matrix is 1. The row wise and the column wise it is also 1. If it is O, O means there is no relationship, then the reachability matrix will be 0. In the row wise it is 0. And the column wise also it is 0. Now see. Very interesting. Now you see, first diagonally each elements are 1, 1, 1, 1, 1. See, this is 1. That is the transitivity. Okay. Right. Now you have mentioned previously, you see, here obviously A, V, V, A. You check it. A, V, V, A. So 0, 0, 1, 1, 0. A, V, V, A. Just you see now. 0, 0, 1, 1, 0. In that way you have to mention. Then 0, 0 means here it is 0. It will be 1. It is 0 means here 1. But it is 1 here. V means it is 0. Again V is there. It is 0. So in that way, you have to substitute the 1 and 0 in the reachability matrix. But please remember, if there is a value x here, x here, then both the side, in the row side, suppose where the x is there, I'll check it. Suppose process automation PA to CDM is x. PA to CDM is x. Now see, PA to CDM, PA to CDM, it is x. Now, CDM to PA, yeah, this value. This is 1 and 1 because this is x. Similarly, if there is the value is O, suppose this value, lack of raw material to the transportation constants. Okay. Transportation is constant, but raw material is not available with the supplier. That is different. Suppose LMM to TC is O. LMM to TC. LMM to TC. Yeah, this is O, means 0. Then TC to LMM. TC to LMM. TC to LMM is also 0. So, first you will fill the first as per the VAXO. Then same column you have to fill it off. Then next column similarly. Then next row. Then next column also obviously will go. Then the third row. So this is the reflection. I have just told why I have filled only one side. Another side will be the reflection of that one. Next, the important feature of the reachability matrix, SAI, significance of AI. What is the driving power? Two things I mentioned. One is driving power, one is dependence. What is that? Driving power means SAI, how many factors it is driving? Means 1, 2, 3, 4, 5, and 6. What is the meaning of V? V means influencing. Second one. So, significance of AI is influencing process automation, revenue generation, centralized decision making, your just-in-time, and product diversification, and including himself. One is by default himself. So, there are 6 driving power. This is the dependence you see. SAI 1, 2, 3, 4, 5, 6, and 7. So this is the 7 dependent. How many 1 here in the column? 1, 2, 3, 4, 5, 6, 7. 7 factors he is dependent. 6 factor he is driving. Similarly, suppose I'll go with LMM, this factor. How many 1 is here in that row? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 factor is driving LMM. But dependent on only 1. LMM. So this is the known as the reachability matrix, where you have to convert into the binary matrix. Second part, you have to find out the driving power and the reachabilities, dependence powers of the each one, each factor. Then third one, we'll go to the very interesting area, that is the label partition. What is the label partition? It is the reachability and the antecedent sets for each factor are found from the final reachability matrix. The reachability matrix already I have here. The reachability set consists of the element itself and other elements. Intersection, here I should tell you three things here directly. It will be easy without the jargons, okay? So these are my 12 factors, okay? These are my 12 factors, the first column. Second is the notation, SAI, UPC, LC, PA, LMM, CDM, all these things. Three columns I have to go for that: reachability set, antecedent set, and intersection set. Three things. What is reachability set? SAI is influencing which factors? These are the reachability set. SAI is dependent on which factors? That's the antecedent set. SAI. Just tell me which factors they are driving. Factor number 4, factor number 5, factor 7, 9, 11. 4, 5, 7, 9, 11. And dependent on SAI, 1, 2, factor 3, factor 6, factor 8, factor 10, factor 12. That I have mentioned. Reachability means influencing. 1, 4, 5, 7, 9, 11. Antecedent set means dependent. 1, 2, 3, 6, 8, 10, 12. Intersection means the commonality between these two. This and this. So what is the commonality between these two? The common term is only one. Here, intersection. That is one. Similarly, suppose I'll go with the RG, suppose, number 5 factor. I'll go with the RG, any factor. Now, you see, the whole row, only one is there. One, you see. What is that? Factor number 5. 1, 2, 3, 4, 5. But if you come to that column, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All factors, they are dependent. Same factor also, because by default, same factor related to the same factor also. So 12. You see, number 5. Only driving 5, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All the factors is dependent. This factor is dependent. So the intersection set is, the common set is 5. So out of these and these, the common sector is 5. Similarly, all the factors you will do in the label partition, the third step. And the 𝗕𝗪𝗪 says they have modified, they have told us, if, please remember, if, very important line, if reachability set and the intersection set having the same value, if reachability set and the intersection set having the same value, that will be the label 1. That will be the label 1, the topmost label. Now you check, where is the, number 5. Number 5, same value, 5 and 5. So this is the label 1. What to do now? Once 5 already over, 5 position you got it, then delete 5 from each value. In reachability set, automatically you will find no 5. You delete 5 from others, and this is already over. Then you check next value, which will be after 5, which other value having the same these. Now you will see 9, 11 here, 5 is deleted, and 9, 11 here. Simply somewhere I have seen. Again 9, 11 here and 9, 11 here. You see. So already 5 deleted. So now this will come under the label number 2. Second label of our model, our diagram, our structural model. Then 9, 11 already over. So you have to delete these two terms 9 and 11 from each word. So 9 and 11 if you delete everywhere. So this is already over 9 and 11. So 9 and 11, you'll get it. Then you see 4 and 7 remaining here. This is 4 and 7. Then here 4 and 7, only 4 and 7. So this is the beauty, you can say. Level 3, they are coming under level 3. Then level 4 came, level 5 also there, level 6, it is there. 7, you see there are 1, 2, 3 levels. All 12 factors, you got their level also. Top level is factor 5. Then second level already you got factor 9 and someone factor 11. So what we did, we have divided this into 4 categories. This is my factor 5F, 5. Then factor 9 and factor 11. I don't know exactly. I have forgotten the JIT and PD. JIT is the factor, PD is 11, JIT is the factor 9. Okay. JIT is factor 9. So this is factor 9 and this is factor 11. So this is the model you got now. First, level 1, level 2, level 3, level 4, level 5, level 6, and level 7. This is the model you have developed through the input only, I'm telling you, through the input only. The interesting part here, the level 7 is known as the bottom level, short-term focus, where the top level is the revenue generation, is my long-term focus. With these things, let me explain I'll interpret the model. Okay, now we have to interpret the model. What is the model says? Lack of resolution, labor constraints, lack of materials and machinery, and transportation constraints. This influences it. Due to this, supply chain disruption is there. Once supply chain is totally disrupted, unavailability of the buyers, because unawareness of the people regarding the COVID, which leads to significance of the artificial intelligence. They lead to. So once significance, you will install the artificial intelligence, so automatically centralized decision making and process automation will come. Obviously, if you will install you will go with the AI, the CDM, centralized decision making, and the process automation. Once these things will be there, you will go with the lean manufacturing and just in time, and just in time will be possible, and product diversification is possible. So in this case, once just in time and product diversification will be there, obviously, finally in the long term, you will get the revenue generation, the company will get the profit. This is the Dr. Runo, can you mute your microphone, please? So now, this is the model you have to interpret. I'm telling you, I'll show you the result and discussions. Another thing is, we are classifying the 12 variables into 4 categories: autonomous, dependent, linkage, and driver. What is that? We have 12 factors, 12 factors, 12 by 12, x-axis, y-axis, you take these things. In the 6, you have to divide all these things. Then there is all the driving power and the dependence here. Factor 1, driving is 6, dependence is 7. So 7, 6. Then these UPC, second factor here, 1 is the dependence and 8 is the this. Then labor constants, the dependence is 1 and this one is 9. So all the driving power and dependence, you have to put it here. Now see, F5. F5, what is the dependence and the driving power? You check. I have mentioned here F5. F5, you check it. F5, your F5, yeah, RG, revenue generation, the dependence is 12. But the driving power is only 1. So now see, the dependence, x-axis is the dependence, so it is 12. Okay, but this is only 1. Similarly, F9, F11. F9 and F11, you see, F9 and F11, 9 and 11, 3, sorry, F9 and 11, just a minute. This is my 9. Yeah. 11 is my dependence, and this is 3. And 11 also, then 11 also, 11 and 3. This is also 11, and this is 3. Where is the 11? Yeah, 11, it is also 3. So if you go with this, you will get F9 and 11 is, it is 11 and this is 3. So this is my point. This factor is coming the dependent area, because more than 6, it is heavily dependent. More than 6 in the driving area, you see F3, F6, F8. F3, F6, F8. F3, when you are going with F3, it is 1 is dependent, but 9 is the driving power. F3, F6. F6 is 1, but here it is 9. So 1, 9, 1, 9, and another is your F8, transportation constants. It is 1, it is 9. So these are the values. Here it is 1. Dependence is 1, but driving is 9. So 3 factors are here. So automatically they are the drivers. They are the bottom of my model. Autonomous means low driving power, low dependence. They are on focus factor. At least in India, not a single factor we got which is unfocused. Okay, because we have not still now given any emphasis towards the area. So there is no factor in the autonomous. Linkage is something different. High dependence, high driving. Only it will be the instability. It will lose the instability. So, yeah, Mr. Arun, can you mute your microphone, please? Arun Kumar Jena, please mute your microphone, please. So, here, linkage I got, you see, F12 and F11, F1. F1 is, I already have remembered, significance of AI, SAI. And what is SAI? And what is F12? I have forgotten. 12 is onability of the bias, okay? F1 and F1 and what just I'll check it. 1 and 12. You see one significance of this is very close to the dependence. It is very close to the dependence. So what? Please try to bring this factor either dependent or you should bring here in the driver. If it will be here, the whole system will be unstable. Slightly changes will be there, means whole our model will be disturbed. How will you interpret that? That in India, artificial intelligence in the inception stage, initial stage. That's why they are not in the driving position. they are not in the top dependent position. They are in the middle way. So now you see the result and discussion. There is no autonomous factor. Autonomous variables means after the weak driver, weak dependent. So these don't have the much influence on the other variables of the system. In our study, there is no unfocused factor because there is no autonomous factor in manufacturing industries. Government of India has started initiative to push the SMEs during the pandemic. Factors like revenue generation, top level, product diversification, top, just in time, product diversification, just in time, central decision making, process automation. These are the weak drivers, but strongly dependent on others. They are seen at the top of the ISM hierarchy, that model. These variables represent the desired objectives of our organization and classified as the dependent variable. They are the top level of our hierarchy. To linkage significance of AI on ability of buyers, you see. These factors have a strong driving power as well as the strong dependence. These factors are unstable due to the fact that any changes occurring to them will have an effect on others and feedback on themselves. So it can be inferred that the interference like that, the significance of AI is remedial measure for unavailability of buyers and the inception stage in it. Factors like labor constraints, lack of materials, transportation constraints, these are at the bottom level, are at the bottom model, which leads to the supply chain disruptions, having the strong driving power. They are driving all the factors. These variables will help the organization to achieve its desired objectives, are classified as the independent variable or the drivers. The starting focus we should give to them. So the variables with the higher driving power and more of the strategic orientation. Thus, performance can be improved by continuous improving the driving variables, continuous these variables, so that we can achieve the digitalization. So significance of the AI, the digital technologies of AI can be applied to tackle major clinical and industrial problems during and after the COVID-19. AI is used to understand the customer demand. Already I have told you trends, the pattern, the forecasting, the predict outcomes. Tata and Maruti, they have started the healthcare equipments during that period because AI has told the trends and basically the forecasting area accurately. So conclusion, the revenue generation is the long-term focus, and you can say, and this AI, which is achieved by the AI, which will give a solution to the labor constraints. The labor constraints, lack of materials, transport constraints are the short-term factors. Incorporating AI, primarily based technologies, into the manufacturing industries may have a considerable impact on the performance of the enterprise. Obviously, the uses of synthetic intelligence efforts is stepped forward performance, reduce cost, optimize the cost. The first slide I have told you, optimization of the cost and better manufacturing flexibility. Because mass customization, we can accept that. So this research will be a guideline for the decision makers of the manufacturing industries. So here, basically in summary, you can say the digitalization is not optional. It is not optional, but a strategic necessity for the modern manufacturing to achieve the efficiency. Efficiency means output by input. We know the productivity, the efficiency. But can we improve with the existing input? The output, can we add much more output with the existing input? Or can we get the same output with reducing the input? Both are the profit for us. So achieve the efficiency, quality, means fitness, standardization, all these things, sustainability issues, and the long-term growth. So this is the basic objective of the digitalization in the manufacturing. Small references I have shown in these things, okay? These are some references, small references. Thanks a lot. Then I'm waiting for the interaction. You want to find this area, the article, to the Elsevier, sciencedirect.com, and I will share my link also. You will get the paper. It is available online. Yeah, the digitalization of this manufacturing area in COVID-19. Thanks a lot. Is it audible to all of you?
Yes, sir. Audible,
Yes,
sir.
sir.
Sure.
Hello.
Yeah, it is audible.
Yes, sir.
So,
Audible. Anyone
thank
having
you
any
for
questions?
being the patience.
Hello.
Yeah, just I'm sharing.
Anyone having any questions?
Yeah. Satish Kumar, thank you. Thank you. 𝗕𝗵𝘂𝗃𝗧𝗔𝗟, thank you for the nice session. Thanks a lot. My dear students, if you have got something, it's my pleasure. Okay.
Thank you. Thank you, sir.
𝗕𝗵𝘂𝗃𝗧𝗟 are rare. 𝗕𝗵𝘂𝗃𝗧𝗟, then 𝗕𝗂𝗃𝗃𝗃, thank you. Audible, sir. Okay, thank you. Excellent. Satish, thank you very much. 𝗕𝗵𝘂𝗃𝗧𝗟, thanks for one session. Thank you. Thank you, sir. Nice session. Any question also you can ask me. You can put me in the chat also if you have any question, please. And let me show my paper. Okay, just a minute. If possible, I'll show you the paper. You can take the pic of that one. Okay, just a minute. Yeah, just a minute. Yeah, just a minute. Digitalization. Yes. Just a minute. 1 minute. Dr. Susri, just a minute. Yeah, it is perhaps I want to share one. Just yeah, can I share 1 minute? Just a minute. 1 minute. Yeah, you can get this paper. Just a minute. Yeah. I want to share these things. Is it visible to all of you? Yeah, you can take this title. It is available. PDF, everything is available online. Okay. So we'll get the total paper and the model, everything what I have explained also, everything in the sciencedirect.com. Okay. Here, the total, the model also here and everything and reachability map, SSIM, reachability, the model, everything is there. Okay. So you can take this topic is slightly enhanced, extended topic is here. Significant digital technology in the manufacturing sector, examination of the key factors during COVID-19. Okay, you can get it here. Okay, take the picture. So now, thanks a lot. Okay.
Thank you
Yeah,
so
it's
much,
up.
sir.
Now the stage is yours, Dr. Susri. Yeah.
Thank you so much, sir, for delivering such an insightful and engaging session. We truly appreciate the time and effort you have devoted to sharing your knowledge with us. On behalf of Dr. 𝗕𝗫𝗄𝗎 and myself, Dr. Susri Ipshita, we extend our sincere gratitude and wish you continued success in your academic and professional endeavors. And sir, we are also looking forward to host you again.
Thank you. Thanks a lot. It's my pleasure. I'm very much thankful to the organizers and whole my my previous, my of the key, while I am the one of the alumni of your organization, Raajdhani Engineering College, was a dean where I have served. The lovely environment, lovely ambience. Thanks, Dr. Khethes and Dr. Susri.
Thank you so much.
Okay, again, and wish you all the best. Thank you.
Thank you so much, sir. Thank you so much.
Can I leave now? Okay.
Yes, sir.
ଆପଣ ଇଏଟା ଅନ୍ କରନ୍ତୁ ଅନ୍ କରନ୍ତୁ ଆପଣ ମୋବାଇଲଟା ଇଏ କରନ୍ତୁ ଆପଣ ବି ଅନ୍ dear participant, hello. Very shortly we will start our validity session. After that you can give your exam 7:15 onwards. And we have a change schedule due to unfortunate case of our ex-principal. That's why we have changed some schedule that first we'll go for validated, then we'll go for exam.
A small doubt, sir. Is exam link will be given in
A 7:15
Zoom meeting or
onwards.
it should be that will be provided in Zoom meeting or in AIC portal, sir? Portal only.
In
Okay,
portal,
sir.
sir. Hello.
Yes, sir. Okay, sir. Okay, sir. Understood, sir.
Actually, our external principal who was no more due to cardiac arrest. Okay, so that's why today is their 12th day. We are very unfortunate. We are missing him. That's why we have changed some schedule. Okay, so 7:15 onwards. So we'll start our validity session. Can we? Hello. 1 minute. 1:50. Is there any stuff? Okay. Hello.
Hello. Sir, where we will get the exam link?
Exam link in the Atal portal.
Atal portal in a test
Yes,
or
yes.
directly in the FTP?
Direct in the
In
test.
Directly in the test.
Yes.
But it has the test marks. It does not have feedback, assessment. Like this, it is given.
Assessment. You will go for the assessment.
Okay, okay, sir.
Click on assessment, you will get
Okay, sir.
question.
Okay, sir. Thank you so much.
Okay, okay. So let we start our validated session now. Distinguished chief guest, respected principal sir, director sir, and esteemed resource persons, my hardworking co-coordinator, Dr. 𝗕𝗏𝗙, and organizing team, mostly important, our dedicated participant. A very good evening to all, and I welcome you for this validatory session. As the coordinator of this 6-day faculty development program, Frontier in Semiconductor and Functional Material, FS-FM 2025. It is my distinct honor to present the concluding report on what has been done in the last 6 days. Over the last 6 days, we have a beautiful journey on semiconductor and functional material and how semiconductor and functional materials is useful in day-to-day life and how it should be included in curricular and co-curricular activity like given by some expert like 𝗕𝗵𝘂𝗹𝘁𝗍𝗏. We started on day 1 with a organic semiconductor and quantum technology with a series of technical session, 13 technical session, and somewhere in some technical session we got also hands-on activity. We navigated through complexity of electric vehicle battery, module park, welding technology, and a recent trend in advanced material throughout this session. We are privileged to host 13 eminent speakers from institutes like IIT Kharagpur, IIT Goa, NIT Rourkela, and industry like Tata Steel, who brought not just theory but a real-world insight into our vision and a classroom. I am proud to share that we had more than 280 participants joining us from different states and different colleges. Thank you, all those participants, for joining this FDP once again. This program would not have been possible without unwavering support of our management and to our principal, who provided us the vision and the resources to execute this event. That's why I am very much thankful for that. To my organizing committee and co-coordinator, thank you for working behind the screen to ensure that technology coordination and scheduling remained seamless. And to our participant, thank you for choosing to invest your time with us. Before we conclude, a few brief announcements regarding the road trip. All participants who have maintained their required attendance, please complete your post-FDP assessment and give the feedback to get your certificate. At last, I want to say that I know education is the movement from darkness to light. I hope this week has ignited a new spark in your academic journey. I wish you all the very best as you take this learning back to our respective classroom and laboratories. I now officially conclude the report of this 6-day FDP program. Thank you. Now I am requesting our esteemed principal sir, Dr. Sanjay Kumar Bera sir, to say something about our joining like 6 days of FDP program. Sir, please.
Honorable dignitaries, respected faculty members and participants. Today is the concluding day of 6 days online faculty development program organized by Department of Mechanical Engineering. It gives me immense pleasure to say that the department has invited resource persons from institutes of repute who share their knowledge, experience, and information to the faculty and participants that help the participants for their future career. My appreciation goes to all faculty members who strived very hard to make it successful. I hope all objectives and outcomes have been achieved. Thank you very much.
Thank you very much.
Thank you very much.
Very much, sir.
Now
Now I am request from participant side.
participants
If anyone interested to say something about our program, please share your views. Participant, please. Participant, please.
Hello.
Yes, hello.
Hello, sir. Good evening, sir.
Good evening.
Your class teachers. नीचे लिखे हैं जवाब है ना गुड इवनिंग सर आज we are conclude our 6-day faculty development program from Atal portal. So thanks a lot to my HOD Dr. 𝗕𝗬𝗪 sir and the co-coordinator of this program Susri Ipsita madam. Thank you madam so much for your effort for the 6 days, and thank you for all the keynote speaker, all the participants and the program coordinator. Also, I would like to give my heartfelt thank you to Principal Sir and the management team for the cooperation. Thank you all. So from this session, we learn lots things which I hope which help for our research work and for our academic career. Thank you all. Thank you, sir.
Okay. Thank you, ma'am.
Welcome, sir.
Interested to anyone interested to say something about? Please. Okay, sir. Please switch on your video. We'll have a group. Dear participant,
please.
video on कीजिए video.
Dear participants, please switch on your video.
No one is doing. Optics are online, auntie.
Okay.
Okay.
Any participant
Any
want to say
participant
something?
want to say something?
So can you please repeat?
Any
Any
participant want
participant want
to say something
to say
about our
something about
activity?
our activity program?
We have tried to
We
give our
try to
best.
give our best.
Okay, thank you.
Okay, thank you.
Now I request
Now I request
our
our
co-coordinator Dr.
co-coordinator Dr. 𝗕𝗫𝗙𝗪
to share his
to
vote of
share his vote of thanks.
and next
And next,
at
at
7:15 you can
7:15
start
you
your
can
exam.
start your exam.
You can assessment.
Hello,
Can
sir.
assessment.
Good
Yes,
evening,
yes,
sir.
Yes,
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 I am
yes,
Akanksha Kale, sir, from Nagpur, JIT Nagpur.
yes, ma'am.
yes, ma'am.
Sir, that session was very nice. I
Okay.
attended all the sessions, and it really very nice and very effective session. Thank you so much, sir.
Thank you, ma'am. Thank
Thank
you,
you,
ma'am.
ma'am. Thank you,
Ma'am,
ma'am.
thank you, ma'am.
Okay.
Okay, ma'am.
Okay. Now, ma'am, can please give the vote of.
Give the vote of
Thank you. So, respected dignitaries, esteemed speakers, faculty members, participants, and dear colleagues, on behalf of the organizing committee of this Atal Online Faculty Development Program, I take this privilege as the co-coordinator to express our heartfelt gratitude to everyone who has contributed to the successful conduct of this Atal Online FTP. As I have already said in the inaugural session, this program would not have been successful without Dr. Alok Mahapatra, who compelled both of us to apply for this program. And we both do really miss him. And he would have been so much happy to see this number of participants and all our resource persons. So we do really miss him. Next, I would like to thank our amazing coordinator of FSFF FDP, Dr. 𝗕𝗫𝗪𝗪𝗛, who has been the backbone of this program. And thank you so much, sir, for your guidance and support throughout. And next, I sincerely thank our distinguished resource persons for their insightful and enriching sessions. Your expertise, dedication, and willingness to share knowledge have added immense value to this FDP and greatly benefited all participants. My heartfelt thanks goes to the Atal Academy, AICT, for their constant support and for providing us with this valuable platform to enhance academic and research excellence. I would like to express my deep appreciation to our college management, our principal, Dr. S.K. Behra, deans, our heads of the departments for their unwavering support and encouragement throughout the program. I also thank the technical team for their dedicated efforts, teamwork, and seamless coordination, which ensured the smooth execution of all sessions. Finally, I sincerely thank all the participants for their enthusiastic participation, active interaction, and valuable feedbacks, which truly made this FDP a success. So once again, thank you all for your support and cooperation. I wish everyone continued success in their academic and professional endeavors. Wishing you all in advance a very happy Christmas and a very happy New Year. Thank you so much.
Thank you, madam. Thank you, sir.
Thank you, madam. Thank you.
Okay, thank you.
Thank you. Wish you the same, madam.
Okay.
Thank you, ma'am. Wish you a very happy new year.
Thank you, ma'am. Thank you, sir, for a very
Okay, same to you.
wonderful session. Happy New Year.
Thank you.
Happy New Year.
Same to you, ma'am.
Thank you, ma'am.
Thank you,
Please,
ma'am. Thank you, sir, and Happy New Year.
Ma'am,
Merry
thank you, sir.
Christmas.
Happy New Year.
sir, don't forget
Happy
to
New
give
Year. Thank you.
assessment. It will
Okay,
start
thank you,
after
ma'am. Thank you,
17
sir.
hours. Actually, we are
Happy
hurrying
New
to
Year.
our what I told you earlier. That case. So please don't forget to give your assessment. Give your assessment and download certificate. And if you are having any problem, I don't think that there will be a problem in attendance. However, fine. If you are having some problem, I will check it and I will update it very soon. If you are having any problem, you can share your thoughts in a WhatsApp group.
Thank you.
Thank you, sir and madam. Now we conclude it. Hope we will meet again. Now you can leave. All participants can read now. Oh. Sir.
Recording stop.
Thank you, Kriti sir.
Thank you. Kriti sir.
Aଜ୍ଞା sir.
କୋଉଠି ଅଛନ୍ତି?
Good sir, good sir.
Thank you madam. Exam ଟା ଦେଇଦେବେ।
ଆଜ୍ଞା ଆଜ୍ଞା।
ହଉ। 7:15 start ହବ।
Sure sure sir, sure.
ଆମେ ଟିକେ ଜଲ୍ଦି ଜଲ୍ଦି ଅଛୁ ତ
ନାଇଁ ନାଇଁ ଠିକ ଅଛି sir, ଆପଣ ଆସନ୍ତୁ।
ସୁଭାଷିଷ sir.
Thank you, Kriti sir.
Thank you, thank you.
Thank you, thank you, Surya sir.
Thank you, sir.
Okay.